Good morning, good afternoon. On behalf of the Vivo Communications Research Institute, welcome to join us today for the launch of our third 6G white paper, 6G Services, Capabilities, and Enabling Technologies. In late 2020, we released two white papers, Digital Life 2030 and Beyond, and 6G Vision Requirements and Challenges. The first white paper showed us many vivid 6G scenarios of people's daily life in 2030 and beyond. The second white paper gave vivo's 6G vision to build a freely connected digital and physical integrated world. In this report, our experts explore the technologies we believe will shape our life in 2030 and beyond. It is an exciting time for our industry. The 5G rollout in full swing and have yet to revolutionize the world in ways we can only imagine. At the same time, we have set our sights on the future 6G. Vivo has been investing time and resources into research and development at the forefront of the 5G evolution. As one of the world's leading smartphone vendors, we've been dedicated to empowering customers by making cutting-edge 5G smartphones affordable and accessible. Vivo has also been actively involved in shaping 5G standards over the years. Standards play a key role in the development of customer devices and allow us to create the digital life future for our users. In 2016, we established the Vivo Communications Research Institute, which focuses on 5G technology research and standardization. Today, our team counts more than 100 global standard experts. So far, we have submitted over 8,000 5G proposals to the third generation partnership projects, leading to 15 technical features and 3 technical projects being approved. Each decade, a new generation of mobile communication technology emerges, and the industry is gradually forming a consensus on 6G and what it might look like. The ability to satisfy people's needs through technological innovation is what motivates our research efforts. We continue exploring what a 6G world looks like and what technologies we need to develop to get there. Finally, please welcome Rakesh Tamaraka. Rakesh is our leading 5G standard expert and drives Vivo's 6G research efforts. He will speak about the latest developments and the exciting future of 6G. Thank you.
Hello everyone, thank you for joining us today. My name is Rakesh Tamrakar. I am a leading specialist at Vivo and responsible for company's 5G and 6G research and development. Today, I'm going to talk about the future 6G communication system. I'll present our views on what services 6G can potentially support, what capabilities are required, what technical breakthroughs are needed to make our 6G vision a reality. These points are elaborated in the white paper we are launching today, 6G Services, Capabilities, and Enabling Technologies. Let's start by exploring the background of wireless mobile communication technologies. To date, wireless mobile communication technology has evolved from first generation to fifth generation. A new generation is introduced roughly every decade. The first 4 generations mainly focus on human communication. The technology developed from voice only to voice plus text and then to multimedia communication. 4G revolutionized mobile internet, leading to a boom in data communication. But 5G is taking wireless mobile communication applications beyond human communication. 5G supports enhanced mobile broadband, ultra-reliable low-latency communication, and massive machine-type communications, opening up many new businesses and vertical industry application opportunities. However, the human desire for new ways of communication, entertainment, lifestyle, working environment, and public services does not stop here. And this is why we are already thinking about 6G. Available statistics show that data traffic in the past decade has seen a sharp increase, doubling in just 2 years. Our digital footprint has gradually penetrated every aspect of life: work, communication, entertainment, production, services, and more. Mobile communication has profoundly changed people's way of life, especially in the post-pandemic era. Smartphone users are expected to consume an average of 15 GB of data per month in 2022 globally. Today, we can easily connect with our loved ones anywhere in the world with high-quality video calls at minimal cost, which was unimaginable just 2 decades ago. And as we continue to refine the technology, we can expect the emergence of holographic communication or telepresence as early as 2030. This will revolutionize every aspect of life, including the way we seek and provide services, the way we work and commute, the way we produce goods, and the way we innovate with high efficiency and a low carbon footprint. With the development of 6G, it will be possible to narrow the digital divide and address the unequal distribution of opportunities. So, what kind of services and applications can be expected from 6G ecosystem? In our previous white papers, we presented our views on digital life beyond 2030 and the vision, requirements, and challenges for 6G. An integrated 6G network will not only connect humans to humans, but it will also connect humans to machines and machines to machines. 6G will help create a whole new digital world. We predict that hundreds of billions of devices will be connected by 2030. Every aspect of our lives will be connected via 6G system. Government services, healthcare, education, and entertainment will all be instantly available on smart devices with the touch of a finger. Industries, transportation, workspace, and homes will all be connected. More people will be able to work remotely. More doctors will be able to treat those most at need through remote treatment methods. And students from any corner of the world, many of whom who may not have had access to education opportunities, will be able to learn remotely. In addition to communication services, the 6G network will also provide computing services to smarter connectivity. For example, a terminal device will be able to request an AI computing service from 6G network to analyze the data it possesses. This kind of smart connectivity will help to provide sensing services for environmental monitoring, health monitoring, traffic monitoring, and more. 6G will expand basic communication services to support completely new experiences, such as immersive mixed reality and holographic and multisensory communications. 6G mobile data connectivity services will continue to improve in capacity, data rate, latency, reliability, and many other aspects. This will broaden the range of users and increase the value of services with more end-to-end flexibility and adaptability to meet the needs of individuals and industries. Meanwhile, 6G will further expand geospatial coverage, lower the access barrier of terminals, and improve the accessibility of connections to connect and freely transmit information between physical and digital worlds. Compared with 5G, which only provides limited information such as user equipment positioning and network information provisioning, 6G will provide wireless sensing and positioning functions, integrate network and terminal operation data information, connect various sensors to collect public data basic, and even integrate public basic information of industries such as Geographic Information System, also known as GIS. 6G will support converged computing capabilities and provide converged computing services, including AI, through computational network convergence technologies. 6G will also have native support for communication, information, and computing services. So, what would be the performance and efficiency indicators? 6G performance indicators refer to the achievable performance of the services provided by the system, which directly affects the service experience of users, whereas 6G efficiency indicators reflect the cost and efficiency of the services provisioned by the 6G systems. Defining reasonable 6G efficiency indicators is a prerequisite to ensuring the sustainable development of the 6G network. Compared with 5G, 6G will further improve communication capabilities. The technology will support advanced applications such as holographic communication, intelligent interaction, immersive XR, unmanned operation, and more. Every performance indicator, such as data rate, including peak data rate and user experience data rate, communication delay, and area traffic capacity, will be improved several folds or more compared with 5G. Coverage is also a very important aspect. 6G will support the full coverage of air, space, and sea via satellite communications and high-altitude platform technologies. In addition to further expanding the terminal access range, 6G will also integrate technologies such as backscatter communication to support very low power terminal communication and improve near-field coverage performance. In addition to user equipment positioning already seen in 5G, 6G will support broader sensing capabilities. From where we stand today, the key performance indicators for 6G system sensing services can be defined as sensing accuracy, sensing resolution, sensing range, sensing latency, and sensing update rate. The range of values of these 6G sensing performance indicators depends on a range of factors: the operating frequency band, system bandwidth, transmitter and receiver structures, number of antennas, and transmission synchronization accuracy of the 6G integrated sensing and communication system. All influence the sensing performance indicators. The right-hand side table here compares the system performance and indicators for various assumptions. For example, the central frequency and bandwidth. The measurement based on radar SNR calculation method and the sensing accuracy calculation method. Varieties of applications can be envisioned with the given performance requirements. On the basis of communication connectivity, the 6G system is able to provide integrated computing services such as computation offload, in-network computing, AI inference, model update, and training. AI performance indicators such as achievable performance, AI model complexity, convergence speed, generalization capability, data dependency, running time, and more, all depend on the progress of the AI technologies. When it comes to defining the computing performance indicator of the 6G system, it is necessary to consider the scenario suitable for 6G computing, as well as the user density of 6G system computing services, computing business models, and many other factors, including the computing performance indicators of users. For interactive 3D virtual digital humans, preliminary calculations show that the computational requirements for rendering are expected to be no less than 10 teraflops for character expression of a highly precise, highly intelligent, interactive virtual digital human with significant amount of data to process. Further, assuming that the density of active users in the high-value scenario is 1 person per 5 square meters and the cell coverage area of 10,000 square meters as an example, the performance metrics required to support these application scenarios are shown here. 5G supports 3 categories of usage scenarios: enhanced mobile broadband, ultra-reliable low-latency communications, and massive machine type of communication. And 6G can further improve each one. We call them eMBB 2.0, URLLC 2.0, and MMTC 2.0. In addition, 6G systems may also feature brand new usage scenarios, such as converged computing, integrated sensing, and more. The 2 figures here highlight the level of importance of performance indicators for different usage scenarios. So, what are the enabling technologies that will allow us to reach this new level of capabilities and services? From new network functionalities to new air interface technology, a whole range of technological innovations is necessary, including further enhancement of existing technologies. Looking at 5G, communication and location services are supported as an integral part of the system. However, computing services are provided by the external cloud or multi-access edge computing as application. 6G will converge communication, computation, and sensing in a single system. This is necessary to enable applications such as immersive XR, holographic communication, multidimensional sensory capabilities, and more. In current systems, communication control plane functions and user plane functions are defined to realize end-to-end communication services. However, new network functions need to be introduced to support new services and achieve integration of sensing and communication. These include a sensing function, computing function, and data function. 6G will converge mobile networks with computing, cross-domain data interaction, and native AI networks. This requires a brand new system architecture design. The 6G network will converge communication and computing functions, which can provide services to users with high computing needs. Computing services include both AI and non-AI computing, such as AI model inference, video rendering, and more. 6G systems can better support computing data transmission by coordinating computing latency and transmission latency. Due to the distributed nature of 6G network nodes, widely distributed communication and computing convergence nodes can shorten the latency of computing data transmission and reduce the transport load of backbone network. For UE computing offload and in-network computing requirements, potential applications include virtual digital human, extended reality, and image or video processing. This UE can select the appropriate computing node and obtain computing services through the 6G system, which means terminal devices can be simpler, lightweight, and consume less power. Up until today, communications and sensing were 2 independent features served by 2 separate technologies. For example, a 4G or 5G system is only for communication, while a radar system is for functions such as speed measurement, sensing, and imaging. The 6G system, on the other hand, will provide a wide range of integrated communication and sensing services by utilizing millimeter wave and terahertz bands. This integrated approach will find applications in smart health services, smart traffic control, natural disaster prevention and response, and much more. We anticipate that both the 6G network and the terminal devices will be capable of sensing. For smooth integration, several aspects should be considered in the system design from the beginning. Notably, Waveform design should take into consideration both communication and sensing requirements. Multi-antenna technology should support high throughput and sensing functionalities, receiver algorithms, interference mitigation, and more. However, there are still many challenges. Some of the obstacles we need to overcome include joint optimization of network, channel modeling, and degradation of sensing performance due to nonlinearities. It can be anticipated that the 6G network will be a very complex system, supporting numerous applications and deployment scenarios. So the system design should be very flexible as well as simple to operate. AI can be an intrinsic part of the 6G system, enhancing network operation to further improve efficiency. AI can play a significant role in network automation, simplification of higher layer protocols, and flexible physical layer design. Networks, as well as terminals, can generate a tremendous amount of data, which can be utilized to train AI models to perform various functions for optimal performance. AI can also address issues such as nonlinearities in power amplifiers, nonlinear interference in physical layer applications, and so on. There could be different levels of collaboration involved between networks and terminals. We envision that AI will be an indispensable part of 6G end-to-end system design. Multi-input, multi-output, also known as MIMO technology, has been key to improving spectral efficiency in wireless systems. It plays a significant role in 3G, 4G, and 5G networks. 5G further supports massive MIMO technology to harvest the millimeter wave spectrum. To support a vast range of spectrum from sub-1 GHz to terahertz bands in 6G, massive MIMO technology will play even greater role. Spatial multiplexing of multiple layers of data transmission to efficient beamforming technology will be vital for optimal utilization of available spectrum. Deployment of an extremely large array in terahertz bands can extend the coverage for extremely high data rates, whereas distributed MIMO in sub-1 GHz allows seamless mobility and cell-free operation, which enhances the interruption-less ubiquitous network availability. Massive MIMO technology will play a vital role in uplink as well, with terminals supporting larger antenna arrays. 5G NR heralded massive machine-type communication services, supporting numerous vertical applications. In future 6G, it is expected that there will be hundreds of billions of connected devices, especially very low-power IoT devices. To support such extremely massive communication, the devices should be very cheap and have ultra-low power or even zero power consumption. These types of devices could support several kbps data rates with a coverage range of 100 meters, as well as sensing and positioning functionalities. There are two broad categories of application from coverage perspective: wider coverage application and local coverage applications. Logistics, environmental monitoring, smart agriculture, smart transportation, smart grid, and industrial IoT devices fall into wider coverage category, whereas smart homes, wearable devices, and health monitoring implants fall into the local coverage category. To unlock all the possibilities that 6G has to offer, we need breakthroughs in several areas. We need to think about how to support higher throughput, new waveform design, support of higher order modulation, increased coverage reliable transmission, interference mitigation, synchronization, multi-user multiplexing, and more. Recently, technology such as Reconfigurable Intelligence Surface, also known as RIS, has drawn a lot of attention in academia and industry due to flexibility in deployment and lower cost. RIS can be a completely passive device or a very low power device that can be controlled to achieve desired outcomes. Electromagnetic properties of each element of RISC can be controlled to steer the reflected beams towards the desired direction, to enhance coverage of millimeter wave deployment, or it can be used to improve MIMO throughput by manipulating the channel characteristics. It can also be used to suppress intercell interference and can be an integral part of network deployment in 6G. However, there are several challenges for real deployment which should be studied as part of 6G research and development. For instance, in a multi-operator scenario in one geographic region, RISC deployment should not impact an adjacent frequency band where another operator has deployed another network. The potential new waveform for 6G is another exciting area for discussion. In particular, a new waveform design known as orthogonal time frequency space, or OTFS, has drawn much attention. Research suggests that the OTFS waveform provides the efficiency needed to support high-speed mobility scenarios, satellite communication, and wireless sensing capabilities. In the OTFS waveform, modulated symbols are mapped to a two-dimensional grid, delay Doppler, known as DD dimensional grid. Due to the channel sparsity in a DD domain, the OTFS waveform provides robust performance, which can reap the benefit of time frequency diversity and can improve overall efficiency. For context, the 5G NR supports the CP-OFDM waveform in a downlink, while both CP-OFDM and DFDS-OFDM waveforms are supported in uplink, and significant performance degradation is observed in moderate vehicular speed. In conclusion, 6G will allow us to bring the next generation of connectivity into every aspect of people's lives. It will integrate more access technologies, cover a large physical space, and provide better core capabilities, supporting more services. 6G will contribute greatly to society, from the democratization of professional talent to the enhancement of emergency and disaster response. 6G is now in the ideation phase, and we have a long and exciting journey to make it a reality. I'd like to invite you all to learn more about vivo's 6G vision in our third white paper, 6G services, capabilities, and enabling technologies, where we elaborate in more details on what services and capabilities can be expected in the 6G systems, outlining several key technologies that are needed to meet the requirements. I hope you enjoy it. Thank you.
Congratulations to Vivo for organizing this 6G panel discussion, theme for now, for the future. In 3GPP, we're now working on 5G Advanced, particularly in terms of Release 18. The RAN Release 18 package was approved last December, aiming for both immediate and longer-term commercial needs. I'm also expecting to see 6G discussion in 3GPP at a certain point in the future. My best wishes for the successful panel discussion. Thank you.
I'm Johan Johansson, the chairman of 3GPP RON Working Group 2. I'm honored to have this opportunity to say a few words to you. We have seen now 40 years of development and evolution, 1G, 2G, 3G, 4G, 5G, and now we're looking forward to 6G. Each of these generations have brought tremendous market success, and for 6G, indeed, we have very high expectations as well. 5G is still under development, and so far, I guess for most end users, it has mainly brought higher bit rates and enabling of mobile gaming by low latencies. But for 5G, there will be more. Support for high-end IoT, support for drones, satellite communication, more advanced private networking. But the main question for today is 6G. 6G, what will it be? From industry perspective, I would say there is no clear answer yet. Maybe 6G will be better support of collaboration using AR, VR, immersive technologies in general. We have all seen during the COVID period the growth of the collaboration apps and the importance of digital collaboration tools. So 6G may bring better support for smartness, artificial intelligence, machine learning. 6G will for sure bring usage of new spectrum. And with this comes the challenges that us peoples in standards are used to try to address the impossibilities of the physical laws and how to make coverage and performance sufficient when it's almost impossible. So indeed, we have high expectations of 6G. Vivo, then. Dear Vivo enthusiasts, Vivo has contributed to and impacted the 5G development and the 4G development in a significant way. And I'd like to congratulate Vivo to this 6G statement of direction, bringing quite many quite tangible proposals and issues into the 6G table. This will need to be considered by the rest of the industry. Thank you.
Thank you all for the wonderful words. We appreciate the recognition of our work. The development of 5G was and is an industry-wide collaborative process. And we know that collaboration will continue to drive progress as we look ahead to the next generation. At Vivo, we are proud to contribute to the industry's push towards a 6G future. So today, I'm honored to share this virtual space with leading experts from our industry and academia. Please help me welcome Dr. Juan Montoyo, VP of Engineering at Qualcomm's Corporate Standards Group, Juan holds a PhD degree in electrical engineering and has been working at Qualcomm in San Diego since January 1997. Currently, Dr. Montoyo works on the design and standardization of 5G NRFAs.
Okay, so hi everyone. Okay, so we move to the presentation already, right?
Right, yeah.
Excellent. Well, thanks, Rakesh. I'm very happy to be here, taking part of this conference on 5G revolution and 6G with Vivo's friends. I mean, thanks again for the invitation and the opportunity. What I'm going to be talking today is a little bit on how Qualcomm sees the transition to 6G and how we see it's actually 5G advanced evolving. So let me get started with where we are in terms of actually yes, the last 30 years of history, 35 years actually. Qualcomm was founded in 1985. So, okay, let me just, okay, very good. So, as I said, I've been in Qualcomm just over 25 years. Qualcomm was founded actually 37 years ago. In 1985, and I've been also fortunate to try the evolution of wireless as it went from this analog to digital conversion on 2G, and then also the rise of the smartphone industry, which for a large extent is even replacing the desktop capability, right? And the smartphones today have the complete capability that we will many years old personal computers would have. And then also wireless communication used to be something only for people, only for voice at a point in time. We have also witnessed this transition to data connectivity as well as interconnecting things, right? I mean, we use Internet of Things or this interconnection of everything with everything else. So it's indeed been a great opportunity to be involved in those. And if you wonder about where we are in terms of actually 5G, 5G keeps growing. It's a reality. In that sense, I think it should be clear to everyone. By now, we have over 220 operators which have already commercially deployed 5G. There are 275 additional operators invested in 5G. And then just to give you an idea, and this is kind of the uniqueness of the cellular industry. Only in 2022, we are expecting to ship over 3 billion 5G smartphones. And if you look into the number of 5G connections by the end of next year, by the end of 2023, we will reach over 1 billion connections, which is, if you put the analogy or in correspondence with what happened in 14 days, it's 2 years faster, so faster pace. And then between 2020 and 2025, we are expecting to ship between over 5 billion 5G smartphones. And then, well, by now, we already have over 1,300 designs, 5G designs, and launched or so those are very impressive numbers, just speaking by themselves. What we have really seen is this drive of the digital transformation across industries. Cellular is not just about interconnecting people, it's about connecting everything with everything else. So we have transportation, manufacturing, industrial, retail, energy, smart cities, public safety, health, agriculture, entertainment. And all these are use cases that are indeed real enjoy the connectivity that 5G offers. So now, we really do how Qualcomm is contributing. Again, I think that Qualcomm, when they joined, we were building GPU systems. They were actually, that was the 2G days of IS-95, where we were building the stations, the suites with the public telephone, also the base station, and then the terminal, the chipsets, right? So we kind of focus more and more on the chip design for the terminal side, but we are trying to get inject a little bit again into contributing to this what we call connected intelligent edge, which is also putting a little bit of emphasis on the greater part of infrastructure. So this is a hopefully we want to see a convergence of wireless connectivity, efficient computing and distributed artificial intelligence, and basically in a sense unleashing this massive amount of data to fuel our digital future. So again, we call this intelligent edge, which is a very, we just trying to bring more smarts towards the edge of the network, and later we will see a little bit more into how we have seen this cloud evolving over the years, over the generations. Of course, there are underlying important aspects like privacy, reliability, and latency, which are also always important. So now, this is being responsible for that. I have to show this slide. I mean, a particular G doesn't come in one shot. I mean, of course, there is a first release, and then that first release with a single project that it gets final with some functionality, semi-functionality. So we already had 3 releases of 5G. We started release 18 just this year, and with that we are seeing the start of 5G, we call 5G Advanced, which is, you can think of it as a second wave of 5G, which will take us towards 6G. When 6G will happen, still is to be decided. There is no discussion so far including about that. It is our view that the 18 and 19 should be exclusively spent on 5G Advanced, and then probably on 20 and beyond, we will start working 6G with the proper study first, and then subsequent normative projects. And then creation of 6G. So now, according to how things came in section of 5G, there were a lot of foundational work for 4G, and a lot of basically things that we tried and we played about around 3GPP for 4G. We were actually there available from the day one of 5G. But I think one very distinctive aspect of 5G, when you compare with 4G being raised to a single actually kind of configuration of the underlying waveform is actually the opportunity to scale for different use cases and different spectrum. So the amount of spectrum that 5G has access to is effectively from 400 gigahertz all the way to 17 to 70 gigahertz. Right? So with a little gap between 7 and 24, which is left out for future study. But yes, there were coding schemes that were introducing 5G, soft rules for gigabit per second connectivity, and then multi-antenna techniques being a very important aspect of any cellular deployment. We actually developed those frequency range one, the 6 sub-7 range, so the FR1 and the code. With massive MIMO, which was in some sense already played in the late days of LTE with this experimental MIMO. And then also for millimeter wave about 24 gigahertz, we have this mobile millimeter wave, which in a sense was the first time that we were using millimeter wave in a mobile environment, not just for the communications that we have seen in the past, either on satellite or terrestrial deployments. Tools have expanded since then. I mean, additional functionality was introduced in 16, the padding on the license, padding on sighting for VPX with initial emphasis, but also padding on the positioning, which was not really supported until 16, and many other aspects that were evolved over the subsequent releases. Release 17 was supposed to be a short release, but then COVID hit us, and it actually got delayed features, and of course there is a good amount of regeneration projects and with support on certain features, but I would like to emphasize 3 particular projects that were adding a functionality that was a device side that was not supported earlier. One was the reach capability in R, which is bringing in R to make more affordable type of form factors. there is expansion in the way above 52 gigahertz up to 71, and then the production of satellite for 5G. There were two projects, one really tailored towards IoT, more on the LTE kind of family of IoT, so now IoT and IoT, and another one taking in our F20 right, satellite networks with a variety of actual deployment options, and whether it is low Earth or geostationary or anything about in between. Releasing and beyond will bring us this new functionality with an interesting balancing of actual priority that we're discussing in a second. Now, moving on into what are the balancing act that CDB was claiming when 5G Advanced was defined. So 5G Advanced is a new label, and it defines a set of projects which start in release in June, but then actually taking into account three very important axes. One is mobile broadband evolution versus vertical expansion. Another one is immediate commercial routes versus longer-term 5G vision. So it is important to realize that unless we stop building certain aspects, there is no capacity to implement anything else. So it is important to start some projects, take a break, and then start some new ones. And we have a good share of actually important projects. And then enabling new type of devices as well as an evolution of the also we will see important in some of the projects. In here, we have a high-level summary of some of the projects. I mean, some of them are really tailoring those mobile network operators. So advancements on mobile, whether it's a download mobility and coverage, that is one area. Is the data matter of several operations. There are measures to try to ease 5G network deployments. So I in a feature that was introduced in release 16 as a cell backbone so distributed unit of the network that is it doesn't have a wire to a central unit, which is going mobile in release 17. So this cell actually could actually and provide coverage for users within that vehicle, for example, as well as in the vicinity of that vehicle inside. There is another network node which we were putting as a smart repeaters, and it's being called by network control computers, which is another attempt to bring get another option for low cost type of deployments to extend the coverage of the network. So, as we move from frequencies, we see that we are really banking on those multi-antenna techniques, and both the 3.5 or 4 gigahertz as well as the deployments. But there is an inherent reduction on propagation conditions, like in the sense that the propagation or power loss increases with higher frequency. So in that sense, it is important to come up with economical viable ways to extend the coverage of networks for 5G. Another project of importance is multiplexing. It's in academia being included all forms of full duplex, so enabling transmission and reception on the same resources. There is they will be first step in the security that we're going to look into some cell-time separation that is happening around transmissions, which actually would solve some of the deficiencies of 2D deployments that maybe going to by increased latency compared to having availability of having resources at all times, as well as a better coverage, because in TDD, we will only try to run out of instances versus maybe the possibility of running every single instance. AI/ML, I'll talk about it in a second. It's a big part of 5G Advanced, and it's going to be a part of CG. And it will be able to also really implement It was considered in release 15 when the 5G was introduced, because there are very few signals that have to be transmitted by the network. So the network has plenty of opportunities to represent and save power. Also, making, by the way, the terminals were high, because it's less signals to watch on and to monitor. But then in release 18, we are going to have this project that we're looking to how to model this energy consumption in the network side, as well as how we're going to try to improve it. And then looking into growth, I mean, our proliferation of 5G in new devices, we have XR being one very important area. We have RedCap or scalability in our line evolution. We're trying to go for further reduce complexity. I talked about silent introduced in 2016. It's in February 17, and we want to really explore it and then try to find use cases for 18 and above. And then, well, enhancements on provision, enhancements on multicast, and then enhancements on other type of communications, terrestrial, so drones, as well as satellite communications, with some important enhancements and to just make them even more effective. So now, if we look into zooming into 5G AI, so again, I think this is going to be a good segue into the next discussion on 6G. So AI is being discussed in community for some time. It came to the radio groups for the first time in the recent future. It's a project that actually has a pretty complete objective. First is we identified when developing the project a set of use cases, and we want to now zoom in and get them as complete as possible. But some projects, interface projects, were identified as CSI feedback, so channel state information feedback, big management, and positioning accuracy. And then we're going to look into those as effectively pilot use cases for how PDPP would enable improve effectively end user experience, right, and improve performance. Considering potentially non-conventional implementations that would rely on these artificial intelligence algorithms, right? So there will be a lot of discussion on the models, the implementation itself. There will be an understanding of what will be required to describe. There will be also some discussion on how we're going to evaluate the performance and how we compare with respect to as I said, conventional type of techniques. And then we will try to see where is the specification, how will 3D need to chime in and show impact in the specifications. I mean, to some extent, it's a really open-ended, but I think open-ended in the sense that nobody knows to a full extent how much we will expose our this AI and ML radio kind of solution space. But there are certain aspects that for sure will surface at the very least some configuration, some actually how our things going to be tested, how our things going to be operating, and several other aspects like that. How much, how 3D will enable the possibility to either exchange models or data models as the terminal and the network themselves realize that things can be evolved and improved. There is another part importantly also for AI now, which basically resides just below the network, which effectively it's an evolution of this data collection, where the devices will send data to the network, and the network will actually try to make sense out of that, to make intelligent decisions on certain aspects. So mobility, load balancing, and energy savings are considered as three main use cases. And then there will be other use cases coming out later in the days. As a whole, right now, we want to see network architectural advancements that enable this AI/ML. Procedural enhancements that will also enable this possibility to do some management of the underlying AI models, how to also enable maybe a better training and a greater influence as if both sides are aware that indeed this is what we want to do. And then how do you manage the data, like then identifying also some of the use cases. We have a few of them already identified, as I said, in ways of doing that, but those are definitely some of the people that like. So moving on into another area which I believe was important, I think, for the audience is to work with those IoT devices and services. Yes, there's another area. We have industrial IoT, we have regular IoT, we have, let me definitely try to start from the top. So industrial IoT is very high performance, very reliable, low latency, and then we sensing and network operation. So fixed links, for example, are crucial, right? There are these are addressed to some extent in release 16 with the introduction of some important enhancements on URLC as well as the introduction of TSN. As I said, in release 17, we should have cap, which actually is going to try to offer a low-cost version of NR. NR CPs, it was introduced in 15 with very high radio capabilities and data, like 40 antennas on most of the new bands, as well as 100 megahertz. And release 17 enables the possibility to go to single receive antennas, which are much more highly for example, wearables, but also to 20 megahertz. That is going to evolve in release 18 into a farther and evolve again up. We are still seeing the outcome of that, but people talk about they reducing farther the bandwidth to 5 megahertz from 20. It could have been a baseline reduction, a big rate reduction, or it could also entail some RF reduction, narrowband operation. But also, people talk about protocol, I mean, making a protocol, like a protocol in support of these devices. In context to the massive MTC type of solution space that typically has offered traditional from 2013, we will see MTC and other where are available, those were introduced for the purpose of delivering these low power wide area deployments. So those were designed for increased coverage, which Red Hat was not really designed for. Red Hat was really for lower complexity, lower reduced capability. And then there is another new layer we don't discuss more in this presentation, but I think we could also importance for 2016 is this other lower end type of devices below narrowband IoT, which is already 180 kilohertz type system. That gives you an idea of the bandwidth of the data that it supports, which would actually go to these passive devices that do not really rely on batteries, right? Or they have maybe a battery that gets recharged from the waves, from the waves themselves. This is another aspect that is important. Some of this energy harvesting and type of technique could be applicable to release 19, backup evolution, so on. That's yet another interesting area. Moving on, now getting into the transition to CBT, we have a physical world. Everybody is fully aware of what the physical world is about. We divide that physical world to make it consumable to things, to machines, right? And this creates this digital world. And more now we are creating this distribution or we call it here spatial computation to make it also consumable to human beings. They are make the physical world into one of those virtual world, which effectively enables these immersive interactions and effectively takes this human communication to the next level, right? So we believe this gets introduced in fact advanced with some of the XR applications, but this will be from day one available in CP. It's these human interfaces are present with physical digital. Now, this I mentioned very briefly over the cloud and the role that it plays into the network operation. I'll go back to 40 days. Maybe there was more and more regional clouds. We have seen this getting closer to the edge, renewable edges getting introduced for certain applications in 5G. And then actually we could even think that some of the applications on these convergence or rails that I just mentioned will even require a closer cell site even edge, where compute will be somewhat in between the terminal devices and that cell site edge compute capability. Which I thought it was interesting. Now, in order to proceed, there are areas of evolution where we see advances are needed. And new generations come roughly every decade. There are advancements in RF, there are advances in compute. There is a more solid disaggregation of the radio. There is this machine learning component, a native machine learning component, where the radio and the learnings from the radio will actually produce the way it's sent over the air. And then, of course, advancements on silicon and material technology are of importance. Advancements on the temperature phase, we still have to see with AR, XR glasses or technology displays or goggles becoming mainstream. I think we will see this in the next years. And then power, right? I mean, power is critical for the network. It is critical also for some devices, in particular these new form factors like glasses. And then, of course, multimedia, display, graphics, and so on. Right? Then we see all those applicable to, again, extreme evolution of XR experiences, improved role of vehicles, and then new topics that have not even been identified. So these are the 6 pillars for 6G that bottom now the leaves are of importance. One is, again, with AI now, power end-to-end communications, with spectrum expansion and sharing. So we are going to, of course, tap on this, high frequency, 100 gigahertz, but also we will try to see an expansion of this coverage area to higher frequencies, right? Because the coverage areas right now are typical for every plants, they're on the lower side of the spectrum, the bandwidths are typically very limited. We will probably see expansion of this vertical group for environmental awareness. And then on radio, of course, everything with energy will be up for discussion, the typical waveform as well as coding, but also how do we expand these monopoly needs and how do we do this very high spectrum and operation method. It's being managed by how we currently do for the algorithm. Emerging models is something I already mentioned. First, we will use virtual to enable these massive interactions between human and then world around them. And then, a scalable network architecture and communication resiliency. Another very important aspect of every generation is this security. So there are robust resilient security, basically intolerant to failures and attacks. I mean, there's aspects like the post-quantum security of importance for 6G. And we will now wrap it up, just to wrap it up, we see a continued evolution. As we said, more and more we are hearing two aspects. Another aspect, by the way, is on deployment. There are all these new materials, there are these reflective intelligent surfaces, and many other type of nodes that we actually surface into the new deployments that actually seems to be offered. But the 5G is working. We are entering a new chapter with 5G Advanced, and those will take a direct impact or direct. They will have and we will offer a direct impact to the day one of 6G. And I think with this, I will just complete the presentation. I want to thank you all, and then open up. I don't know whether occasionally have any time for any questions or thank you.
Please help me welcome Mr. Satish Jamadagni, Vice President and Head of Standards at Reliance Jio. Satish is also the Vice Chair of TSDSI, India's Standards Development Organization. With 23 years of industry experience, Satish boasts around 200 granted patents in the wireless and network domain.
Thank you, Rakesh. Thanks for the opportunity. So let me start off with 5G. Some of the learnings that we had from 5G and how they can influence the 6G specifications going forward. So some of the key observations that we had from 5G are related to some of the most fundamental aspects of any wireless telecommunication network, which is spectral efficiency gains, which are offered by the technology, and some of the issues like coverage, concerns on coverage. So these are the two major aspects that we have looked at very critically. And what we find is, in comparison to LTE, and you can see that the comparison between LTE and 5G NR from a spectral efficiency perspective, we see that both the air interfaces are same. So essentially, we are seeing around 15 to 20%, depends on the nature of implementation of the scheduler and other things, but something in the order of about 15 to 20% gains. Now compare that with some of the cost figures that we get to see in comparison between the two, LTE versus, there's a substantial increase in the cost figures. So there has to be a proportional increase in the spectral efficiency for it to make business sense. And that's one of the key understandings that we have acquired so far from 5G trial or 5G analysis perspective. And this is one of the key learnings from 5G. When we go to 6G, we want to have the spectral efficiency and some of the coverage issues to be orders of magnitude higher than what we find in 5G, irrespective of the nature of the band deployment. There are technologies available which can enable this, so that's not so much of a concern. Say, for example, if you go from mid-band to higher band, there's still ways in which the spectral efficiency and the coverage concerns can be met, because in some sense they both go hand in hand, because spectral efficiency, sometimes you can meet the spectral efficiency in the center of the cell, but not necessarily in the edge of the cell. So you need to have coverage and spectral efficiency concerns going hand in hand. There are ways in which it can be done, and from a 6G perspective, there has been discussions with respect to intelligent reflective surfaces, essentially some kind of a relay technology which will enhance the cell coverage area or the cell diameter or radius. This is one of the key first observation I'd like to put forth. The other key aspect is the cost of deployment of 5G. If you look at the cost of deployment of 5G, these are GSMA numbers. So it is estimated that globally, if LTE coverage has to be met by 5G, something around $1.3 trillion has to be spent. And this is not even taking into account some of the regions today which is not covered by LTE. Africa, for example, South America to some extent, Southeast Asia. Some of these regions are not accounted for in these calculations. So this is one of the key concerns that we have. And if you look at the enabling technologies, there are ways in which this can be addressed. You can have a network architecture which will allow for incremental deployment. For example, you don't necessarily have to put in the capex day one. And there are different models in which operations can come in, the ownership of spectrum. That means the technologies like spectrum sharing has to be built into the protocol stack. And there are multiple ways in which it can be done. I don't want to get into that, but then essentially the ask from 6G is very, very clear. That is, the capex and the opex costs are to be taken into account from day one, from the design perspective itself. And that is something that is very critical for the deployment of 6G. Then we have the other issues that we want to bring about in terms of observation. The 5G network was essentially, at least the initial design was around mobile broadband, what is called as EMBB. So essentially, the 5G network is EMBB centric. But the understanding is, by the time you have a very mature 5G network, which is really bringing in the money, 80% of the data is supposed to be coming from machine types, because much of the expansion is expected to be in the enterprise and in the other segments, which is essentially machine-centric in terms of the data origination. So if you look at a stable scenario, when 5G becomes a cash cow, it's not so much a developing technology, but then again, it is a cash cow. 80% of the data is supposed to be coming from machine types. But then the network was never designed intrinsically for machine type communication. It was primarily intended for mobile broadband, and then machine type is an afterthought. Incrementally, it's being added in the next releases and stuff. So incremental versus intrinsically built, there is a big difference. So that is something that we want addressed as part of 6G. This is again a critical observation from our side. So from TSDSI, which is also Reliance Jio has been spearheading much of the activities in TSDSI on the 6G front. So I can also qualify this as the Reliance Jio vision. What we look at is there is an ask for intelligent mobile connected society, much towards what we have in 5G, but then again taking it towards the digitization of just about every single aspect of human activity. That is well understood. There is a common consensus about this. You ask any vendor, operator, this is something that everybody will tweet. So this is something which is well understood. But there are certain things that we do want to emphasize, and that is technologies will have to address the digital divide issue. And this goes back to the same issue of CAPEX and OPEX as well, to some extent. If you have the cost of deployment of 5G or 6G network in this case comes down drastically, then you have suddenly a lot more geographies investing into this. And that is something that can be enabled through technology and through the right design of the overall architecture. And we believe that is something that has to be done. Now, looking at it from the end user perspective, there is a lot of personalization that can be done. So that is also something that has to be addressed as part of the overall 6G design. When I say personalization, it is both for the comfort of the end user and also monetization opportunities for the operator. And it is addressing both issues. So that is something that we do want to look at. And then we have connectivity, compute, which is all fine, but then the underlying issue is the data ownership sensitivities. Now, in order to explain this, let me just give you a simple example. Now, if you have a 5G network rolled out, which is also supposed to, there's a lot of buzz about private networks and stuff. Essentially, most of the governments and companies and the common population understand that 5G will enable smart cities and a few of these other digitization activities. When you look at smart cities, there are multiple entities to it. There is government, semi-government, private, public. There is a telecom service provider who's only one part of the story. Then there might be a cloud service provider who collects all the data. There might be satellite data which is coming in, which may be owned by a government entity. And then there are departments like pollution board and other entities which are government owned. So essentially, you have to bring all of this data together. That means there is a host of data sensitivities, data ownership issues, data issues that will have to be addressed. If, say, for example, a 6G network will have to intrinsically fit into these kind of deployment scenarios. It's very critical. It's very critical. And this has to be built into the protocol stack. I mean, it cannot be an afterthought where I throw open a certain set of REST APIs and, job is done. It doesn't work that way. This is something that has to be very critically understood and built into 6G, because this is what will enable true digitization, and 6G will have to enable this. And getting into the details of each of these so-called pillars, as I explained, 6G network is not going to be just operator to consumer kind of a business. It's going to be business to business. It is headed in that direction, or it is the wish list is that it heads in that direction, because it is from a business point of view, it is far more lucrative, and it includes a lot more opportunities for all incumbents involved. So this is one of the key issues that we look at. It's going to be some kind of a heterogeneous network. It's going to be some kind of a network of networks. I'm using these terms very loosely, but then they can actually be pegged into specific network architectures. So there are technologies available to enable this. So that is something that we're keenly looking at. Having said that, there is a certain specific way in which networks will have to evolve from day one if you have to include application, the gamut of applications that we see here, holographic communication at one end, extreme high bandwidth requirements to extreme low bandwidth requirements for IoT devices, sensors, all of them having different data ownerships, which is an additional thing over and above what we can accommodate in the existing network architecture. And these are things which will have to be taken into account. A digital divide, yes, this is very critical for us. So what we visualize is this is a combination of multiple technologies, all the way from your Open RAN, openness, to your ability in the network architecture to allow for slow growth, add-on growth, or what we call as small growth. It should also allow for additional issues like account for spectrum sharing, because spectrum is one of the biggest concerns. Much of the cost of any network affordability actually goes into the spectrum purchase. That is one of the key things. Energy efficiency as well, because if you look at the bill, the dollar bill that the big companies who own data servers get to foot, it's a pretty large amount of money that they shell out just to have the energy affordability for all the data centers. Now, if we visualize the same data centers are moving down the hierarchy in a telecommunication network, obviously much of the dollar figures will get translated into telecommunication network. So that is something that has to be taken into account. And not everything in this energy efficiency factor is standardizable. There's a lot of other things which goes into it, but then there is a substantial amount of standardization. It can help. So we keenly look at this space as well. And so there's been a lot of discussion about AI, inherent AI networks, which is 6G. But if you look at it that way, I just want to give you one context from the Indian perspective, not necessarily India. I mean, I'm familiar with this geography, so I'm just quoting this. But then again, even Europe, for example, there's so many small countries, localized cultures, localized habits. If you look at the intrinsics of AI itself, there are two aspects to the AI. Generic AI algorithms which we find today that has to be understood. One is specialization and one is generalization. If you say Google has a data center somewhere in the US and all of the world's data is getting accumulated there, and you run the algorithms, it gets into a generalization mode, which is a hodgepodge of cultures, understanding. It's a gross generalization. It can never be a generalization which comes out from specialization. So AI algorithms always work best intrinsically on small sets of data specific to a certain geography. When I say geography, I'm also referring to the specific cultures and whatever food habits and rest of the stuff which comes in, and that the origination of data adds up to all this stuff. So this is one of the key things that will have to be taken into account. So the whole notion of specialization has to be addressed, or it intrinsically adds up if we have a hierarchy of network of network kind of a hierarchical structure built in. That means there's a data hierarchy built into the network architecture itself. Then you have a realizable intrinsically an AI architecture which renders itself to the intrinsics of AI algorithms. And that is something that we would like to keenly take into 6G in terms of the overall architecture. Make sure that it is built such a way that all of these issues are addressed. And just continuing on the same lines, we can talk of, in order to enable all of these things, we can talk of network of networks, hierarchical data slash telecommunication network, data breakout mechanism, so that enterprises can break out data at any point in the network based on the data ownership and other concerns that there may be. And today, edge is a centralized entity, even though it is supposed to be edge. It is still part of the core network, visualized as part of the core network. Theoretically, in theory, you can always drag it back into the RAN network. If you look at the 3GPP 5G architecture, that's how it is. But then, see, it is more on the paper. You don't find vendors even remotely looking at it in that direction. So, a couple of more emphasis on the use of AI in 6G. of course, we want AI built across the stack so that we can not necessarily use AI for the maintenance of the network, but also be in a position to give AI as a service to other entities or applications which are sitting inside the network. For example, in our data centers or in the edge or whatever it is. So that having said, of course, AI has its role to play in automation and AI analytics. That means the self-healing or the self-maintenance of the network is also very critical from a dollar perspective. And that's also something that has to be re-emphasized. It does continue to tread the path, and this is something that we continue to look at 6G to make it more intrinsic. Now, there was a base 3GPP specification, and then there was a ORAN forum which was constructed, ORAN Alliance, which was brought together in place. And then they came up with something called as a radio intelligent controller, which is much of an afterthought. Some of the concern still remains because once it is an afterthought, you always have to interface and what is the data available for such an entity which can do AI, how much of data you can push from an existing 3GPP network to an external entity, security issues, and all these things are there. Not that they cannot be addressed, but then it does exist, of course. So essentially, we want to have that intrinsically built into 6G. And one of the other key aspects, which I think there is general consensus, especially because you've attended the ITU sessions recently, there seems to be some kind of consensus across all the incumbents or the interested parties in trying to merge communication and sensing. Because today, especially if you have a massive MIMO system, 5G is supposed to be a massive MIMO system, you can always have a certain amount of sensing capabilities built into it. And this obviously opens up a lot more opportunities for the operator and for the end user as well. So this is something that's an aspect that we will look at very keenly from a 6G perspective. There are multiple ways of doing sensing. Sensing, this is a discussion which has already started in 3GPP, but then it's going to take a lot of time, which goes into. One can even think of, you have communication radio sensing and you have image sensing, all the way from fusion of such kind of data to just having radio sensing, which makes a lot of sense and still can cover a lot of application use cases. Just a small understanding of a small note on what we understand on the spectrum for 6G. Though there is a lot of discussion around terahertz band, but what we see is for 6G, we still need some kind of a mid-band spectrum to anchor 6G. We will always have millimeter, we will always have terahertz, but those are the fringe elements. You will need to have some, sane band on which you can anchor the technology, and that's going to be the mid band. When we talk of spectrum in 6G, this holds some significance because there's a lot more that can be done actually. There are a lot of technologies with respect to self-interference handling, which is improved over the years, which we call as full duplex, and they allow for multiple parties or multiple technologies to reuse a certain part of the spectrum, which was not necessarily the case earlier. I mean, it was still there, but I mean, not to the extent that was expected to be. Now we have all those opportunities. Now, how do they play out from a spectrum point of view for 6G is something that has to be looked into. And if it has to be enabled, then obviously it has to be built into the protocol stack. That means spectrum sharing and whatever other mechanisms that needs to be handled will have to be handled at the specification level itself. And this is one of the key elements for us. Spectrum is a concern. A lot of times, spectrum non-availability of spectrum or early allocation of spectrum to some areas, which is not necessarily revenue earning, but then it has been allocated, so it's just stuck. Kind of a scenario can be easily handled with these kind of technologies. The owners of such technology development will be on 6G. I just want to talk about a few other things, issues. One of them is UAV. Just taking a specific example. Why I talk of UAV, because this also lends itself into what is also being termed as a codeless network. Codeless network primarily because it has multiple use cases, fairly independent. That means you can have quick private network deployments, you can have disaster recovery and all those things. Then again, UAVs also. I mean, today UAVs are not fully realized because you really don't have any base station flying out there. But even if you do have some of the specifications are there, and the nature of the specification is that it takes an existing cellular network as a via media. Any UAV control application is seen more as an application. It is sitting either in the core or outside of the core. And there are a lot more regulatory issues which will come in, which is specific to every single country. And that is also something that has to be taken into account. If the capabilities of drones will have to be enabled to their potential, these are the aspects which will have to be addressed. And this also will render itself to codeless networks, which will render itself to enterprise, private, and other segments of business opportunities. And this is interesting, and I think this is also something which is getting standardized or getting into as one of the requirements from the ITU perspective. Sustainability, of course, this hits the dollar amount as well. So, I mean, of course, everybody talks about sustainability. From the Indian perspective, the Honorable Prime Minister of India has made a commitment for a certain amount of carbon reduction, emission reduction. And obviously, 6G will have to take this into account. 6G will have to do its part. It's not just 6G. There are a lot more what we call ITC technologies which will have to cater to this. But yeah, 6G specifications will have to be conscious of the fact that these are certain numbers which have been pledged already in terms to meet certain of these requirements. So in summary, we have learnings from 6G. 5G, sorry, we have learnings from 5G, which will have to be taken into account into 6G. Broadly speaking, we have technology challenges, which are much easier to handle. There are a lot more social concerns which are coming onto the table, which will come through ITU. I'm sure that is happening because it's already under discussion in ITU. And these social concerns will have to see technological solutions in forums like 3GPP or any other standardization body. Then there are other issues like data ownership issues, data personalization issues, which will also enable a lot more services, which also will have to build into the network architecture. So in summary, there are two broad classes of concerns that 6G will have to address. One is, of course, technology. One is coming from the services point of view, personalization and whatever other service enablement perspective. The other one is coming purely from a social concern perspective. And in summary, this is precisely what we are looking at. And as outlined, these are some of the challenges we want addressed in 6G. And we will, of course, be Reliance Jio will continue to or continues to be one of the interested parties, and we will be engaged in this direction. Thank you, Rakesh. Back to you.
Please help me welcome Professor Ta-Ching Chang. Chang is Chair Professor at Peking University in China, with over 280 technical papers published in leading conferences and journals. His work on context model and Wi-Fi based sensing theory is widely accepted by the pervasive computing, mobile computing, and service computing communities.
Okay, very good afternoon, everyone. Today, actually, it's a great pleasure to share our recent work on integrated sensing and communication for 6G wireless network. So the outline of my talk today includes the following 5 parts. First, I will introduce what is the 5G and 6G wireless network, and then we'll talk about the integrated sensing and communication in 6G. Then I will present some technical challenges in 6G ASIC research, followed by some of our recent development with Wi-Fi, 4G, 5G signals. And in the end, I will give the conclusion. So as we all know, in the past 40 years, the wireless cellular network has evolved from the first generation to 5th generation. Actually, in the 1980s, actually the first generation cellular network used analog technology, and then gradually evolved to second generation, which began to use digital technology, and gradually moved to 3G, 4G, and 5G. Right now, with higher transmission rate and a lower latency. So as we know, the fifth generation, right now we are in the era of fifth generation wireless network. And the 5G features three main characteristics. First, actually eMBB mainly for extreme data rates and massive data transfer, which can enable a lot of applications ranging from media delivery to online gaming. And the second characteristic is MTC for connectivity to countless network enabled devices. Basically, it could connect to a large number of IoT devices, then including actuators, sensors, trackers, and wearable devices. And the third characteristic is the URLLC for ultra reliable low latency communication, which could enable high reliability, ultra low latency, and high availability for different kind of applications ranging from augmented reality, mobile robots, motion control, remote control, and so on. So we could see that those powerful features of a 5th generation cellular network enable a lot of potential applications. But even though the 5th generation wireless network is very powerful, but it still cannot meet the requirements for the next generation, which is the 6G wireless network, including location accuracy and the sensing requirement, because in the next generation, 6G generation wireless network, we are expecting to have more accurate localization accuracy and higher data rate, higher reliability, and the lower latency, as shown in this figure. So because the 5G wireless network cannot offer all those capabilities, so that's why we need to develop new technologies to enable the 6G wireless network. Actually, in this regard, there are three possible potential aspects we could enhance the existing 5G wireless network, so-called the beyond 5G or 6G, actually including these three parts. First, we expect enhanced or more powerful communication performance. Basically, it's a plus on top of this current 5G three characteristics. On top of this, we also expect to have integrated sensing and communication, which is called ESAC, and also the AI intelligence to enable more intelligent data transfer as well as sensing. So now I will talk about what is integrated sensing and communication in 6G wireless network. So integrated sensing and communications refer to the design paradigm and enabling technologies that combine sensing and communication systems to utilize wireless resources efficiently for their mutual benefits. Actually, for ASIC, we could support two kinds of sensing paradigm. One is active sensing, which the users need to carry a device. So it's a kind of device-based sensing technology. With the mobile phones, we could localize every user's location and certain kind of activities. And another type of sensing paradigm is called passive sensing, where the users do not need to carry any devices. So it's called device-free sensing, where the users just move around in the environment, and we can sense the user's location as well as their activities. Besides localization and sensing, also, for the integrated sensing and communication, we need to consider, several scenarios. The first scenario actually is the transmitter and the receiver, they are co-located. In such a case, it looks like a radar, and it can sense the human being and the vehicles in the surrounding environment. Another scenario actually is distributed transceivers, where the transmitter and the receivers, they are distributed located in different places. In such a way, we need to collect information from different receivers for sensing. In the above two situations, in the above two actually scenarios, the communications could help, the sensing in several aspects. First, using the communication wireless signals, we could enable a lot of sensing applications, ranging from localization to physiological, kind of parameter monitoring, vital sign monitoring, to environmental monitoring, human sensing, vehicle sensing, and so on. So basically, using the wireless signals, we could support a spectrum of, different sensing applications. On the other hand, the sensing could also help, communication in different ways. For example, we could adjust the communication system parameters using sensing information. For example, when the transmitter and the receiver is blocked by certain things, we could see, we could estimate, we could sense basically there's an obstacle between transmitter and receiver, and we could use different technologies. For example, use the intelligent surface to reflect signals to the receiver. And in such a way, we could still, keep the very good performance of, wireless communication. Besides this, we would also could use the sensing context for beamforming, so that we could focus on certain, direction and a certain, object, so that, we could enable, wireless communication and, sensing in a certain, direction. So for integrated sensing and communication, there are different levels for integration. Basically, the wireless sensing and the wireless communication, they could share the same RF resources, share the same spectrum, because spectrum is very scarce and very expensive. The second level actually is shared hardware, because both sensing and communication need to use wireless signals, so they could share the same set of transmitters and receivers. We could also share the signal processing methods for transmitting signals, for sensing, and for communication. Besides, we could also do a joint design of signal waveform as well as the protocols for sensing and communication. In such a way, we could enable the sensing and communication. They could help each other, on their respective results, based on their respective results. Just now I talked about the integrated sensing and communication in beyond 5G or 6G. Now I'll talk about the challenges we expect to meet in the 6G ISAC research. there are 4 different challenges in this in 6G ASIC research. First of all, we need to design or consider the CSI sampling, considering trade-off between sensing and communication. Because when we do the sensing, sometimes we cannot enable very powerful communication. The vice versa. Sometimes when we do the communication, we cannot support very reliable or very accurate kind of sensing. So due to the requirement of persistent sensing and the nature of random communications, the CSI estimation rate needs to be studied. And right now in 5G wireless network, the CSI sampling rate depends on the density of reference signals. But for the 6G wireless network, we need to think how can we design these reference signals, how can we design the pilot signals, and so on. The second challenge actually is the unsynchronized transceivers and the signals, because in the 6G, 5G wireless network, the transmitters and the receivers, they are not co-located. In such a way, the transmitting and receiving devices will use their own hardware clock for timing and carrier generation. In such a way, the unsynchronized transceivers will generate random phase offset and signal distortion, which would affect sensing or communication. The third challenge actually is the waveform design for sensing and communication. And nowadays, we are mainly using OFDM for wireless communication. But we usually use FMCW for radar sensing. And if we want to combine sensing and communication in the 6G neural network, wireless network, we need to consider what kind of waveform are best for both sensing and communication. And there are several possible candidates. Either we could use OFDM or OTFS or MCW, or design a new kind of wireless waveform for 6G ASIC research. The fourth challenge actually is distributed and networked sensing, because in the future, we have a bunch of transmitters, we have millions of, receivers, and because the transmitter and the receiver, they are in different locations, how can we effectively, combine all the sensing information in the receiver side and the transmission side in the network, so that we could maximize the sensing and the communication performance. Just now I talked about the 4 different challenges in next generation ASIC research, and now I'll also present some of our results in wireless sensing using Wi-Fi, 4G, 5G signals. As we are moving from 5G to 6G, also the Wi-Fi standard is also evolving. And recently, there's a new standard called IEEE 802.11bf, which was, started in September 2020. And the end of last year, 2021, the specification development started. And this new Wi-Fi sensing standard is expected to be completed by 2024. And in this standard, both Wi-Fi communication and the Wi-Fi sensing capabilities are considered. The use cases include smart home, gesture recognition, presence detection, location, localization, gaming control, sneeze sensing, and so on. Why Wi-Fi or 4G, 5G based human sensing is so attractive? Because we all know that the Wi-Fi, 4G, 5G signals, they are everywhere. They are very ubiquitous because they are leveraging the existing infrastructure, the wireless routers, the wireless cell towers, wireless receivers, mobile phones, notebooks, and so on. And so the Wi-Fi or 4G, 5G based wireless sensing is very low cost. And there's no need to wear anything on human body. So it's a kind of no intrusive device-free solution. And compared with the cameras, there's less privacy concern. So that's why Wi-Fi or 4G, 5G based human sensing is very, very appealing. So that's why people begin to propose in the 6G also those kind of sensing capabilities could be operated in the 6G wireless network. In the last 8 years, my team has been working in this area, and we have developed various systems ranging from respiration sensing using Wi-Fi, 4G, 5G signals, or heartbeat monitoring, or gesture recognition, or continuous activity recognition, and the localization and tracking in the indoor environment. We have developed various systems, and those systems could be seen in the next video. The first system, actually, we are using the Wi-Fi signals in our home to monitor the person's heartbeat and respiration rate. So apparently, this kind of functionality can be used for elders staying at home. So we could support more than one people's respiration monitor. With the Wi-Fi or 4G, 5G signals, we could also recognize gesture. We let a person, to that in the air, we could recognize gestures and numbers very accurately. We could also use the Wi-Fi signals, 4G, 5G signals to detect food. This is also very critical for elder care. We could also use the Wi-Fi signals in our home to localize the person's room location. In this case, we could localize person's location very accurately and in real time. We could also do intrusion detection and detect a person's presence as soon as the person enters the room. We could also monitor a person's continuous activity. For sake of time, I will stop here. So just now I talk about some system we have developed using Wi-Fi, 4G, 5G signals to sense human respiration, gesture, fall, intrusion, activities, and so on. And then I will conclude the talk. Actually, as we can see from this talk, actually integrated sensing and communication will be a key feature for the 6G wireless network. And the 6G wireless network is driven by extreme use cases for communication, localization, and sensing, while 5G cannot support these use cases. And so that we have different technical enablers for 6G, including communication, localization, and sensing. And the initial research and the prototyping results for ISAC are quite encouraging, but there are still many challenges and research opportunities for ISAC ahead. Thank you very much. Thank you for your attention.
Next, let me welcome Professor Lingjia Liu. Liu is professor at Bradley Department of Electrical and Computer Engineering and associate director at Wireless at Virginia Tech. He has made numerous technical contributions to major 4G standards and has published over 200 journal publications and conference papers.
Okay, I'm going to present something which we have been doing for a while. So it's actually the title of my presentation is AI-inspired wireless communications, where computing meets MIMO-FDM. As you may know, my name is Lingjia Liu. I'm currently working EC department at Virginia Tech, where I'm also affiliated with Wireless at Virginia Tech, which is a research center focusing on wireless. All right, let's talk about actually. Let's first briefly talk about why AI for wireless. Lots of people talk about why AI for wireless, and so from what we see that AI, we don't want AI to solve the problems we already solved, right? So what we see actually, what AI can potentially solve new problems for us is that as the network, let's say, move from 3G, 4G, 5G, 6G, and network becomes more and more complicated, and there are multiple new knowledges and network coordination. So for those scenarios, especially for very complicated networks, we think actually AI can potentially bring some benefits. And also actually there's another area where AI can potentially bring benefits is actually model deficit. As we know that traditional communication system using a lot of models, right? The first thing that we model the communication system using equation, and then based on that model, then we can do a lot of good things with those models. But there are areas, right, where the model was not available, or even actually is not, let's say, far from being perfect. For example, nonlinear devices. We talk about massive MIMO and low resolution ADCs and power amplifiers. And in those areas, it's very difficult to analytically model those behaviors in a tractable manner. So in those areas, we think AI can potentially help. And also actually algorithm deficient. What does that mean? That means actually in many cases, even though we know the optimal solution, even though very simple cases like Gaussian distribution, Gaussian cases, Gaussian noise, and no maximum likelihood estimator is the best maximum likelihood receiver. But on the other hand, the complexity is far from being, let's say, acceptable. Okay, that's why actually we all know DPC, right? Data paper coding is good for broadcast channel, and in reality, none of us are using it. So why? And because it's too complicated, and potentially actually AI, or especially machine learning and neural network, can potentially help in those areas when we can trade the performance with complexity. Okay, so these are actually three areas we see where AI can play a role, which actually traditional method may fail or may not be that efficient. All right, so we can apply AI and machine learning for various areas. Especially for me, as you may know, I was a 3GPP round 1 delegate. So I was mainly working on finite MAC layer, which I think is a foundational layer. So Rakesh is also from round 1, right? so that's why I think round 1 is the best. The foundational layer. So we want to look at what, let's say, AI and ML can play a role in round 1, right? Finite MAC layer. So for round 1, especially finite MAC layer, we mainly see actually two issues. One is model deficit and algorithm deficit, right? When the network is not that, play that much a role in round 1. And if you look at various important use cases, we see actually we can use AI and machine learning for channel estimation and prediction, where we apply supervised learning, or we can use actually AI for receive processing, for example, symbol detection, right? Detect what is the symbol transmitted. Again, supervised learning. And channel decoding, supervised learning, or we can apply actually machine learning for spatial access, where reinforcement learning now comes to play. I mean, you can think about ACNEC and all those things can serve as a kind of reward, right? I mean, to reinforce the process. And today, our talk will mainly focus on receive processing, even though all those other aspects our group has been actually touched from various aspects. Today, we are going to focus on receive processing, which is symbol detection, and from a supervised learning perspective. So, all right, before we talk about, so previously we talked about AI can help us solve the problem, right? I mean, now before we really go deep dive into it, so we really need to realize actually AI is not a solution for all, right? It has issues. So what are the issues? I mean, it's not actually one thing fit for all. So there are training issues. So what we see is that we think system overhead and availability of training data are two key issues related to training AI models for cellular networks. Why I'm saying this is because, I mean, machine learning has been traditionally used for computer vision networks. Where in those networks, it's very interesting because they are going to train the neural network with thousands of pictures, and then they feed the neural network with, let's say, one or two pictures, let the neural network tell you whether this is a cat or dog. On the other hand, for communication, it's completely opposite. So what you are going to do is that you are going to train the neural network with a few pictures, right? And then the same thousands of pictures, let it tell you 0 or 1, right? I mean, if you recall, I guess many of the attendants are kind of round 1 or actually 3GPP delegates. I mean, if you recall, from LTE to LTE Advanced, release 8, release 9 to release 10, the first thing we do is that we cut the reference signal, right? We cut the CIS to CSIS and DMIS. Why? Because we overhead. And so, I mean, training is actually non-information at the receiver side, which is treated as overhead, right? The communication, the whole purpose of communication is sending things which is unknown at the receiver. So that is a big issue. So how to make AI work with very limited training? That is a big issue. And also there's lack of bounding performance and a lack of explainability. All those are kind of general for most applications. And another thing, that uncertainty in generalization, meaning actually you want the training and the testing have the same feature. Because if the training feature and testing feature are completely different, then, well, it won't work, right? And unfortunately, especially for cellular net, what happened is that not only the environment is changing, it's actually out of picture, it's not that. And because actually transmission mode interference, right? I mean, think about how many transmission modes we have, how many layers we have. I mean, right? I mean, rank adaptation, link adaptation, it's actually dynamic. So if you want to do completely offline training and then, hope it will work on online with all those modes and link and the rank adaptation, probably it's not going to fly. So, I mean, this is something probably we're going to discuss on later, but uncertainty in generalization is very important. Last is lack of interoperability. This is very important for cellular networks because we want different modules from different vendors will work, right? So these are the several challenges. Let's keep in mind from technical perspective, we want to focus on first and the fourth issues. All right, now let's look at the problem. What is a problem? Symbol detection. So what traditional people do is that we transmit X and then receive Y, and then we have a model between X and Y, right? And then from what is known signal, which is actually, let's say, pilot, which is known to the transmitter receiver, and from actually receiving Y corresponding to that X, we can actually try to estimate channel, first trying to estimate H, and then do the symbol detection. What does that mean? We're going to see it more clearly in this particular slides. So if you assume everything is ideal, MIMO FDM system, the input-output relationship is Yi equals to Hi plus Ni, right? H tilde, Y tilde. Those are related to the pilots. So you first do channel estimation. Basically, you're trying to estimate H based on what you have, X tilde and Y tilde. X tilde is your transmitted pilot, and the Y tilde is corresponding received signal. And then you can, various methods, you can do D square, LMMSE, those methods, to try to estimate H hat. And once you have H hat, then you look at those data symbols, right? And then based on H hat and then the Yi, which corresponding to receive signal for the data symbol, then you're trying to extract what is X hat, right? This is actually the traditional way of doing things. Two-step approach, channel estimation, symbol detection, right? And what if the world is not ideal? So we make it ideal, right? We're trying to assume it's ideal. And if the world is not ideal, then we have different methods to make it ideal. For example, DPD, right? Pre-distortion. to actually, we know actually power amplifier is nonlinear, so let's try to actually do some pre-processing upfront to make it look like linear. Right? These are the traditional way of doing things. All right, then let's look at a machine learning way of doing things. So, I mean, from machine learning perspective, right? If you ask a machine learning guy, and then he said, "Wow, this is supervised learning. So what is that? You know X, you know Y, right? Which is corresponding to X. I don't care what is the relationship. I feed this Y into a neural network and train it such that I get X, right? I mean, it's pretty straightforward. It's pretty natural. So, I mean, it seems that it will work, but what are the issues? The issue is that, I mean, you require a lot of training data, right? I mean, you have a neural network, you need a lot of training data, or require intensive offline training. And the problem is that, I mean, like I was mentioned previously, that the pilot is very limited, right? If you want to have a lot of pilots, then it defeats the purpose. And that's why, I mean, the first thing you do is that cut the pilot, you get performance gain immediately, right? So, and all right, these are big issue. Another issue is the online versus offline. Why I'm saying that, I mean, online computer vision problems, right? I mean, wireless communication dynamic is time and frequency, or FDM, right? There are a lot of operation modes in wireless cellular networks. And for example, even for LTE advanced, right, you have rank adaptation, link adaptation, and also adaptation is done on subframe basis, meaning actually scheduling is done off subframe basis, right? I mean, the interference will be different from subframe to subframe. So you're going to do offline training, good luck, right? I mean, with all those data you have, I mean, good luck with that. So, and generalization, problem, right? Uncertainty in generalization will be a problem. So if you are going to completely rely on offline training for receive processing, may be very dangerous. In fact, I would say majority of the work in the academia, in literature, is assuming offline training. Okay, they are using offline training to do this process, which, I mean, as round one delegates more than 10 years ago, I think, well, it's not going to fly. Okay, so we are going to do something which is meaningful, let's put it this way. So that's why we're going to design, it's desirable to have online training based, right? Online learning based receive processing for robust and adaptive communication. So what do we do? So ideally, we want it to be subframe by subframe, meaning actually you just train using a subframe, the training symbol within that subframe, and then detection within that subframe. Okay, because we know within subframe the operation mode doesn't change, right? And also actually interference probably keep relatively stable. All right, so now actually let's look at what kind of neural network we should choose. We should choose recurrent neural network. Why? Because it's actually time, right? There's a recurrent feature into the neural network which has captured the temporal correlation, which is very critical for, let's say, OFDM systems, which is transmitted over time. Right? But only recurrent neural network is very challenging. So on top of that, there are three major issues we see. The first major issue is that over-the-air training is limited system overhead, right? We say we want this to be as little as possible. So in order for us, let's say, to use a neural network-based approach to compare with traditional signal processing-based approach, we want to make sure the overhead is the same, right? Otherwise, I mean, come on, it's not an apple-to-apple comparison. And if you're saying that I have used a lot of training for neural network, and for traditional network, I use let's say, the reference signal, the existing reference signal, it doesn't make any sense. You have to make sure the training overhead is the same, right? Overhead is the same. So this is the first challenge, very limited. And the second is that recurrent neural network process time domain signals, and OFDMs transmit over frequency, so you need to combine some domain knowledge. So you cannot just use brute force, let's say, neural network or whatever, use it, take it as it is to do it. So we probably need to do some combined domain knowledge to make it efficient. The third is that while this environment is changing dynamic over time and frequency, the neural network model needs to be sophisticated enough to capture that variation. But on the other hand, it's actually contradicts with challenge one. Basically, challenge one is saying that, I mean, training is limited. If you have a very complicated neural network, you are going to have overfitting for sure, right? So these two challenges are clearly competing with each other. So what are the solutions? So our solution, so these are actually just simple. I mean, I think for vivo actually experts, this is pretty much too easy, right? These are just to showcase actually over-the-air training overhead is relatively simple, relatively small. This is for LTE advanced kind of reference signal structure. Basically, just to give you a picture that, I mean, it's around 10 to 15% at the most. And this is actually for Wi-Fi, right? Wi-Fi, you have a long training sequence, short training sequence, and then you have pilot amount data. So basically, these are showing you case it's very limited. So what is our solution? Our solution is we're going to utilize something called reservoir computing. Reservoir computing is a novel computing paradigm. Okay, so there are three categories within this. It's called echo state network, liquid state machine, and delay feedback reservoir. And reservoir computing has been shown to be capable of actually doing a lot of things, actually not in the wireless communication domain, but mainly in the speech recognition. Basically, they can capture the temporal correlation. And the nice thing about reservoir computing is that it's very simple efficiency. Basically, you don't need much training. And we are among the first group to, let's say, to look at reservoir computing and apply this to communication. And we're going to show you some of our findings. So a particular reservoir computing we'll look at is called echo-state network, where actually you can think about this is actually the set of neurons. These are actually the internal. This is a recurrent neural network with the recurrent weights, and this is output weights, output neurons, output layer. So you can think about there are three layers. I mean, input layer and recurrent layer and the output layer. So you can think about. So there are four actually weight matrices you can think about. One is input weight matrix, internal weight matrices, output weight matrix, and feedback weight matrices. The good thing that, interesting thing that, among all those four weight matrices, there's only one weight matrix that is trainable, which is actually output weight matrices. All others are randomly generated and fixed. What does that mean? That means actually they don't need to be trained. Okay, so what is that? So maybe at first sight you may think, wow, it's not training, come on. And so you can think this way, like a human being, right? So if your brain is trained enough, it's trained already, so your neurons within your brain is not changing, okay? But when you're observing, right, you're observing the environment, it's actually changing very fast. So this is mimic like this. And also, actually, we are working with Dr. Li Zhongzhen from MIT to look at actually insights of this, which is very interesting because we actually identify if you have a lot of training data, infinity, let's say, large number of training data, you can train everything. You can train all the weights. But what if you have unlimited training data? You want to focus on your training data on the most critical part where actually this kind of fixed random projection is a good projection already. Okay, so and then all you need to do is that you want to actually project from the high dimensional space back to the low dimensional space where actually the output weight is doing. Anyway, so you want to satisfy the echo state property, and which I'm listed here, and to make sure it's stable. And then let's go back to the direct result. Okay, so these are the different pilot patterns we consider. So for simplicity, you can think about A pilot pattern, very simple. Okay, B pilot pattern is also something we extended. Basically, both works. Okay, so but A is pretty simple. So it's a 4x4 MIMO systems. And then we have actually this is a one subframe. Okay, each subframe, the first 4 FTM symbol is pilot. And then, okay, we can extend it to the comb structure, which is B. So we actually developed several computing-based symbol detectors, and this is the first one. There's a window to increase the memory of the real-time computing. This is actually the second one. And later on, we extended to MIMO FDM systems, which is 4x4 for this case. So just look at results. This is a MIMO FDM systems 4x4. QPSK, you can clearly see that, if you're using reservoir computing, is actually already better compared with LMMSE, channel estimation, MMSE receipt processing. Okay, so this is actually let's say this is the PA input power where the linear region. So go here, then it becomes nonlinear region. Okay, so you can clearly see that, the machine learning based approach, you can go deep into the nonlinear region. So here, whatever we mentioned here is all apple-to-apple comparison, basically only utilize the training, limited training in there, in each pilot. Because this is for 16 QAM, you can clearly see that, so reservoir computing-based approach works very well. Go deep into the, let's say, nonlinear region. And later, this is actually the first level of result we show, and later on, actually, we extend this to time frequency reservoir computing and deep time reservoir computing and deep time frequency reservoir computing, meaning actually we explore the structure. Previously, every processing is done in the time domain. So now we have actually been doing down both time and frequency domain. So, and this is a pilot pattern. Simplified pilot pattern we show, and this is a very interesting result. So instead of doing this kind of tap delay model, we use SCM channel, which is 3GPP, widely used channel. And later on, actually, we also look at a CDL channel. Anyway, so for this channel, as you can clearly see that, LMMSE-based approach, this is actually reservoir computing-based approach. This is a fair decoding-based approach. So you can clearly see that in the low SNR region, relative low SNR region, the machine learning-based approach can even beat sphere decoding-based approach, mainly because actually sphere decoding-based approach, we don't assume perfect channel knowledge. So we assume that you have to estimate the channel, right, from the pilots. So that's why actually we suffer from. And also, if you look at the low SNR, when you go to the power amplifier nonlinear region, then you can clearly see straight decoding based approach will actually completely collapse, right? And while on the other hand, the learning based approach will stay pretty stable. And this is actually, we look at low resolution ADCs, so 1-bit quantization and 2-bit quantization. You can clearly see that our strategy, learning-based approach, is much better compared with actually, let's say, traditional signal processing-based approach, which is coincides what we was talking about earlier, right? Where there's no model, right? Model deficit. Here, 2-bit quantization. And this is actually a relatively comprehensive comparison talking about what is overhead we have and how actually the training error and testing errors and for various actually machine learning based approach. And as you may see, actually here for 4x4 MIMO, we have using 23.5% overhead. I mean, so this is just a very brute force way. I mean, of course, we can do more delegation, more deliberated result later. Brute force way is 4 training symbols. Okay, so you can clearly see that it will work. And and on top of that, so here, so far, what I mentioned is that symbol by symbol, is subframe by subframe. So we are saying that it's online learning, it's subframe by subframe basis. Basically, once trained, the neural network will be used to conduct a symbol detection for all the OFDM symbol within that subframe. Okay, for the next subframe, you are going to do it again. So basically, there's no generalization error, I mean, within that subframe, because you're only using that subframes. On the other hand, you can do real-time machine learning. What we do by real-time that we can train it and conduct OFDM symbol by symbol basis. So basically, instead of waiting for the whole subframe to train, and you can actually do a OFDM symbol by symbol kind of detection, and you are going to adaptively change the neural network weights. Okay, so this is actually we did this over a Wi-Fi systems which is clear that so each symbol we only use these 4 pilots to do the symbol detection for this particular symbol, and then for the new pilots that comes in, we are going to adapt the neural network weights and then conduct the symbol detection for this. So this is what we did for Wi-Fi systems, and in fact, actually, not only we did it, we also implemented it in soft-defined radio, okay, in the SDRs. So we have a SDR demo showing actually, so basically, apple-to-apple comparison. What does that mean? That we have a standard Wi-Fi transmitter. It doesn't matter. So you just have a Wi-Fi transmitter. That's it. And then you have 2 receivers. One is a standard Wi-Fi receiver, another is actually a reservoir computing-based receiver. By this, we mean that we don't change anything, right? We did not add any pilots, we did not add anything. Okay, so then you do these 2 receivers simultaneously, kind of receive what's going on. So this is actually result we show. Actually, you can see single kind of machine learning-based approach can beat the traditional Wi-Fi receiver. Okay, in various in different methods. So this is actually what we have been showing. And on top of that, we even do hardware. So not only do the SDR, so we even do the FPGA. Okay, so we do actually more like a FPGA hardware implementation to this. And this is actually our testbed build. So it's a real-time machine learning SDR platform, which actually we have Xilinx actually FPGA to show it's running in the hardware. And you can clearly see that, the software, this is actually the different, these are different actually, different cases, but you can clearly see this is software ESN, this is hardware basically using Xilinx FPGA. And I think it's 11-bit quantization, but I can dig out more. So basically, you can see that, we can kind of trade off performance. Performance is a little bit worse if you're using hardware because of the fixed point, right? But on the other hand, the energy efficiency is much better. So this is our SDR implementation for MIMO FDN. So basically, we were able to do 2x2 MIMO. And now we can do 4x4 MIMO in our group. So 4x4 MIMO completely decouple these 4 data streams using machine learning-based approach. And can perform even better. So this is for multi-user MIMO. So basically, you can clearly see this is done in the pandemic where actually my student did a experiment in his dorm. You can clearly see, right? You have transmitters and receivers in multiple places. And then using actually reservoir computing-based approach or machine learning-based approach, you can do actually multi-user. All right, I think that's pretty much it. Let me conclude my talk. Reservoir computing is introduced for MIMO FDM systems, and instead of conducting channel estimation and symbol detection, and the reservoir computing and machine learning approach allow us to do the conduct symbol detection directly. And we were able to conduct some kind of complexity analysis showing that by doing this, you actually reduce the complexity significantly. And also some interesting observations that reservoir computing can achieve better performance than MRS-based receiver, and the reservoir computing symbol detection achieve better energy efficiency. Okay, so combining neural network and learning approach for telecommunication, I think is promising, and a lot of opportunities ahead if we are going to apply it to relevant problems in a smart way. So I think the keywords is really relevant and smart, right? All right, that's pretty much it. And thank you.
Now, let me welcome Professor Radhakrishnan Ganti. Radha is an associate professor at the Indian Institute of Technology, Madras. Recipient of several awards, Professor Radha is the principal investigator in the 5G testbed project from IIT Madras and was instrumental in developing the RAN part of the end-to-end 5G indigenous system.
So thank you, Rakesh, for the warm introduction. It's a pleasure to be here. So today I'm going to speak about what is going to happen after 5G, some possible technologies, and in particular, I'm going to focus on something called full duplex. Before that, I would briefly spend a little bit of time on 5G, what are its advantages and a few of its drawbacks. And based on that, we will discuss what, I mean, at least in my opinion, what is going to happen in 6G. So, in my opinion, there are 5 key technologies of 5G. Okay, one is the waveforms, better signals, OFDM. Essentially, the difference in 5G is, of course, you have a lot more subcarrier spacing and a lot more flexibility in the way you can pack your frequency and time domain data. So that's what I call as better signals. The second key technologies are the efficient transmission, which is the massive MIMO. Okay, so in 5G, you can transmit on multiple ports. Effectively, you can have a large number of antennas in an array. The third important thing that's very much different from 4G is the green signaling, what I call is the UV-oriented design. Unlike in 4G, which is a more base station-oriented design, 5G is more a UV-oriented design where the reference signals are all based on a UV specific. So instead of transmitting all the time and all the subcarriers, I mean, you transmit these specific reference signals in particular for a particular UV when the UV is on. Okay, this would help you to save a lot of energy, specifically if the number of users are small enough. The fourth point is the faster response. Effectively, the whole 5G system, both the physical layer, the L2 and the core network have been optimized in such a way that you should be able to get a sub-millisecond latency. Okay, of course, a lot more work has to be done on this, but at least the protocol is designed in such a way. So, for example, on the physical layer part, you can change your subcarrier spacing so that you don't have to wait too long before you can decode data. Of course, one of the most important things is the larger bandwidth. So the bandwidth that are supported by 5G has been increased both at sub-6 gigahertz as well as millimeter wave. So in sub-6 gigahertz, you have 100 megahertz bandwidth. Each carrier can go up to 100 megahertz, whereas in millimeter wave, you can do up to 400 megahertz bandwidth. Okay, so this is like a 5x increase, almost a 5x increase in terms of bandwidth compared to 4G. Of course, there are a lot more small enhancements, but I believe that these are the 5 most important key features of 5G, and these features enable us to meet the IMT 2020 requirements, which a lot of you might have seen. This is the Jane spider diagram that has been put up in IMT 2020 vision. Okay, so these 5 key technologies have to be supported by all 5G deployments. If you have to enjoy 5G to its fullest extent and you want to milk 5G so that it performs the best, all these technologies have to be supported. I just want to now list out a few of the good things about 5G and a few things that I believe can be improved going forward. So 5G should not be thought of as something that's going to replace 4G. It is something that's an evolution of 4G. Essentially, it's a new framework, completely new framework, in which we have 10 more years to fill and improve it upon. Okay, it's a vision for this decade. So it has lots, and people who work in 5G understand that there's lots and lots of flexibility to provide in 5G. Okay, I mean, there's so many things that you can do in 5G that are not possible in 4G in terms of configuration. So it also enables multiple heterogeneous networks to coexist. For example, millimeter wave and sub-6 gigahertz to coexist. Even 5G also provides for non-3GPP network, non-3GPP networks to coexist with 3GPP networks, such as interact working with Wi-Fi. It also provides an option of small enterprise level networks. This is akin to small cells, but small cells were mainly about RF, whereas private networks are something more than RF. They have core network involved, slicing, so many other beautiful things that are put in there. And of course, the way the whole spec is written is that technically a lot of things can be moved to software, except for a few things in the physical layer. A lot of processing can happen in software. So this helps in a faster change of the specification. Okay? And it provides support to multiple diverse verticals. Unlike LTE, which is more a data-driven network, 5G provides support for verticals that span from mission type communication, high-speed broadband networks through sensing. A lot of things are possible. There are so many features that are there. But all these features also make life complicated for both developers as well as network operators. So let me just list out a few things. Massive MIMO. Okay, so MIMO is a very integral part of 5G. Okay, it's a very, very important part of 5G. There are a lot of gains that have been promised by massive MIMO. I mean, of course, at least theoretically, they were very impressive. But there are lots of practical issues that still has to be solved. For example, channel feedback. To use a large MIMO array, you require a lot of feedback. So this feedback overheads are huge in 5G. Of course, there's been some solutions provided, but a lot more work has to be done. TD antenna calibration. All the systems are moving into TD systems. So how to utilize the reciprocity of the channel to utilize the uplink feedback for the downlink. Okay? So what I have been hearing from news reports and through colleagues is that the gain of using this massive MIMO is restricted to 3x or maybe at max 4x. It's not scaling with respect to the number of antennas. Okay, this is something that has, a lot more work has to be put in, and we have to understand how to make sure that the gains scale with the number of antennas, because the costs are scaling linearly with the antennas. And the thing is, another major negative point that I have about 5G is the too much configuration flexibility. It's too complicated a specification. Okay, we understand. While this is a boon, it's also a bane. The amount of configuration that's provided in 5G is too much. The next important, I think a factor that has to be thought about in 6G specifically is that we are talking about larger and larger and larger bandwidths. And in addition with this, we are also talking about carrier aggregation. Okay, so while these bandwidths and other things are very nice in terms of scaling your data rates, implementation, battery life, all these things are taking a huge hit when you scale to this large bandwidth. This is a point that requires thorough investigation before we jump into terahertz communication with gigabits of bandwidth. One major promise of 5G is the MMTC, massive mission type communication. But still, if you look at all the deployments and what is happening in the market, still NB-IoT is the choice of MMTC. Okay, MMTC has really not taken off as is promised by 5G. This is in 6G at least. MMTC should be part of the specification. It should not be a separate standard parallel implementation. Okay. So one thing about 5G is the higher and higher frequency implementation. Okay. So when you move higher and higher into frequency, even at sub 6 gigahertz to 3.5 gigahertz, there's a lot of coverage hit. Okay. So while the 5G standard talks a lot about data rates, latencies, and other things, coverage has been something that I feel that has been neglected in 5G. And some emphasis should be placed on coverage going forward, because as my previous speakers have pointed out, the digital divide has to be broken, and it's important for this. Coverage is a very, very important metric, specifically at higher frequencies. Okay. So with this, I want to look at some technologies that people are talking about for 6G. Okay, nothing is fixed in 6G as of now. It's all at this point my own thoughts and what I read in the literature. So what is being touted as potential candidates for 6G are very large MIMO configurations. You're talking about 1024 antenna panels. Okay, you're talking about intelligent reflective surfaces. Essentially, it's things which change your channel. Talking about full duplex communication, essentially, this is something I'm going to talk a little bit more later in the next few slides. very high frequency communications. So in 5G, you have moved to millimeter wave, which is about 26 gigahertz to 40 gigahertz. Now in 6G, people are looking at 100 plus gigahertz to terahertz range communication. Also looking at free space optics to be part of 6G. Quantum security is a lot of work is being done in quantum security to be integrated in the upcoming next generation standards. AI-based communication is something that's very, very interesting. It's going to change the way we are going to look at how we design our pilots, how we do our channel estimation. Already there's a lot of study work that's going on in 3GPP on this AI-based communication. I think that this is going to happen in a 6G given the amount of AI work that's happening across the world. And the convergence of satellite and cellular communication, again, this is already that's happening. We don't have to wait for 6G. In 5G plus itself, it's happening. But in 6G, I think it's going to be ubiquitous. Okay. So why are we talking about all these technologies? So some of the use cases are tactile internet. Essentially, you want to feel, you want to smell, you want to do all those things of your physical sensors should be active on internet. So that is what people are aiming for in the next generation technologies. Holographic communication is essentially 3D rendering of people, 3D rendering of objects on through the networks. AI connected AI societies, all connected AI societies. Effectively, you want everything to be connected. All the gadgets, human beings, machines, all of them seamlessly interoperating with each other and exchanging data and making our life better. At least this is a dream. But these are all the use cases that people are talking for 6G. Automated transportation, of course, this is something that's happening, and human-machine interactions. Okay. So the use cases are also going to get refined as time progresses, as well as the technologies are also going to become mature, and we'll know in a few more years what are the things that are going to make it to 6G. But for now, a lot of work has started in all these areas, and so what is actually going to decide what is going to go into 6G? One is the level of maturity for the technology. Okay? So this is something that's evident through millimeter wave networks. So in 5G, a lot of work has been done in for millimeter wave, but even then there are lots of engineering issues that are still unresolved. For example, uplink transmit power on the cell phone for a millimeter wave system is still a big challenge. Okay, so in terms of nodes, in terms of process technology, in terms of the availability of chips, we have to understand what is the maturity of that particular technology. Okay? And the other important feature is the cost. Okay? Finally, as one of the earlier speakers pointed out, cost is a very important factor in driving all these technologies. Okay? If it's too expensive, it's never going to, it's not going to be widely adopted. Okay? It's going to be adopted only in few pockets. So the maturity of the technology and the cost are interrelated, but this is something that has to be taken into account before we standardize anything. Okay, of course, volume reduces the cost, but other than that, process and the technology also plays a very critical role. And finally, we should also try to have a real use of the technology. We can't just introduce technologies at higher frequency bands just because they are there. Okay. So we should have good use cases, something that are more concrete and related to the real world. Okay, maybe of course we can dream a little bit, but we should be grounded to reality. Okay? One thing we should keep in mind that going forward in a cell phone, 5G, this 6G, all this communication is just one small IC of a plethora of ICs and technologies that go into a cell phone. Okay, so you should understand that people are paying for a lot more in cell phone than just for communication. Okay, with that in mind, we should understand, we should focus on what technologies can become part of 6G, and based on, we should also look at what are the shortcomings of 5G and use those lessons to drive our 6G. So with this, I want to talk about a specific technology, full duplex. Okay, at least my personal belief is that this is an idea, this is a technology that people have been working almost in the last 7 to 8 years. It's an idea whose time has come. Okay, I'll tell you what are the restrictions as we go forward, but it's already being talked in 3GPP. Some work is happening in 3GPP on this full duplex idea. So what exactly is full duplex? So current wireless devices are inherently half duplex. Okay, so if you think about cellular system, you have both uplink and downlink. So the both uplink and downlink happen either in different frequency or in different time. Okay, you don't generally notice this because things happen so fast, but they are separated either in time or frequency. Okay, so they are inherently half duplex. What exactly we mean by full duplex is both uplink and downlink, or transmission and reception, should happen simultaneously in the same frequency band. What is the gain because of this? You can immediately see that the amount of resources that you have just double. Okay, so given the amount of spectrum scarcity that you're talking about in the lower bands, good range bands, you can see that if you can able to achieve this kind of full duplex node, then you can immediately double your throughputs and you are effectively using your spectrum twice as efficient as before. The question is, if it's such a simple idea, why is it so difficult? Why haven't people implemented this till now? Okay. At least from the wireless perspective, this is because of something called self-interference. So you are transmitting a signal at such a high power. I'm just taking an example of Wi-Fi here, but you can extrapolate this to even cell phones or base stations, where the transmit signal is 1 billion times more stronger than a receive signal. Okay, billion is a small, actually on the lower bound, actually it's much more stronger. So you're talking about a very huge signal on the same frequency, which is going to come and interfere with your receive signal. Okay? So this causes us two problems. One is the self-interference problem, and the second is the saturation. Because of the large dynamic range, your front end of the transceiver chain generally saturates. Okay? If you are able to solve this problem in a reasonable manner with a low cost and reasonable technology, then you should be able to realize this full duplex. Okay? So just to give an idea of what is the numbers that you're talking about, I gave you an example of Wi-Fi here. So if you're building your transmitter and the receiver on the same IC or the same board, and you're transmitting at 20 dBm transmit power, you see that there's a lot of crosstalk between your transmit and the receiver. Here, this crosstalk is indicated in this, right, at different power levels that hits your receiver chain. Okay, so when this happens, what happens is your entire receiver chain saturates. Once your receiver chain saturates, then there's no signal, there's nothing that you can be able to decode or transmit information. Okay, so you can immediately see that this is both a hardware problem as a software problem. I'll tell you about the software issues later, but at least you can see that there's significant amount of work that has to be done on the hardware so that you can realize a full duplex. But this is not it. This is what happens on your chip or on your board or in your device. But actually, there's something that happens on the outside also, that once you transmit and receive in the same frequency, same time, you would say your information goes and hits the neighboring reflectors and gets back into your receiver. Okay. While in the previous slide, whatever I have shown are deterministic in the sense that once you design everything is fixed, including the interference leakage. This is very random. You don't know where your reflectors are, depending on how you hold your phone or where your base station is placed. These reflectors change, and the self-interference, the delays and the attenuations change with the self-interference. Okay. So, how do you realize a full duplex? What are the things that you require? Okay. So you require about 100 to 110 dB of self-interference cancellation. Okay, so a part of this has to be done in the analog domains. Just now I told you that if you don't do that, then your front end will completely be saturated and you'll not be able to do anything in the digital domain. Some things has to be done in the digital domain, about 35 to 50 dB, depending upon your use case. The most important thing is this should be robust enough to self-interference multipath. Okay, essentially this should operate in any environment you throw your device. You can't say that your cell phone or design, whatever you design, should take this into consideration. So just one mathematical slide. So if you think about this, what is your self-interference? If x of t is the RF signal that you are transmitting, that's a thing that is coming in from PA. This x of t is going to come from different paths. It's going to get reflected from walls, buildings, anywhere, and come back to your receiver. Okay. So tau k, if tau k is the delay of each path k, you have x of t minus tau k is the received signal from the kth path. Ak is the gain of the path. So you get a summation of all these things. All these things get aggregated. So what is your goal? your goal is to remove this self-interference I of t. But the bad thing is, except for x of t, you do not know how many paths are there, what is the gain of each path, what is the delay of any of these paths. Okay? So this is where the challenge is. The challenge is that you don't know a lot of parameters in the self-interference. Okay? Somehow you have to recreate all the self-interference and completely eliminate that. Okay? So what is the basic idea in all this full duplex systems? The only idea is that you know that what you transmitted. Okay, here in this case, what you transmitted is x of t. Okay, so you know x of t is what is transmitted, but what you are getting is not x of t, but I of t. So the question is, how do you make your x of t? How do you use your x of t to replicate I of t and subtract it off? Okay, so that's one problem. A second problem is, in digital domain, you have x and you subtract x, you get 0. But in analog domain, you subtract those signals, you will never get 0. You will get a very, very, very smaller version of this, maybe 30 dB, 40 dB lower. Okay, so you have to solve these two problems, but your only tool is that you know x. Okay, so all the self-interference node cancellations use this fact that you know x and somehow try to eliminate your self-interference. So this is one thing. One thing is you should know your self-interference. The next thing is, a lot of work has to be done in understanding the channel propagation models of your self-interference. Okay, unlike normal interference and normal channel models, self-interference happens because of echoes from your antennas itself. Okay, you see sub-nanosecond echoes, you see tens of nanoseconds of echoes and hundreds of nanoseconds of echoes. Okay, one is directly in your circuits, the other is close to ground reflections, and the third is far off echoes. So a lot of propagation model studies have to be taken up. Okay, we have done a few studies in our labs and we have published this works. But more studies have to be taken in a general settings to understand this self-interference clusters. Once you have an idea of these clusters, you can design much better algorithms for self-interference cancellation. What are the other issues? The other issues are that your PAs, the power amplifiers, your circuits are all non-ideal. Okay, I mean, if you take a typical transmit circuit or receive circuit, you have IQ imbalances, you have PA non-linearities, you have DC subcarrier problems. Okay, so with all these things put together, somehow you should replicate your I of t, the self-interference, and cancel it. Okay, so there's a lot of work that has been happened in the literature from in the last 5 years on how to model all these and somehow get to the 100, 110 dB cancellation. Okay. So if you think about full duplex in 5G, if you look at 4G networks, in 4G, the TD structure, so in full duplex by definition is transmit, receive, same time, same frequency. If you look at 4G, in 4G, the number of TD structures are very limited. There are 7 TD structures that are possible. But in 5G, the number of the TD configuration flexibility is enormous. You can do so many things with that. Okay, so theoretically, at least you can enable TD, you can enable full duplex in 5G. Okay, theoretically it's possible. Of course, there's a lot of RAN 4 level studies that have to be taken. Okay, already 3GPP is slowly moving towards this. One is based on this integrated access and backhaul. There's a second study item on flexible TAD. So all these are precursors to having a complete full duplex solution, either in 5G, I mean, going in forward in the releases or in 6G. Okay. And initially, the thought process is that this full duplex will initially happen in the base station, okay? Because that's, that seems to provide more gain for the buck, okay? And do you really want to combine full duplex with massive MIMO? I don't think that is necessary, okay? I don't think we should combine all the technologies to make a mishmash of things which you cannot implement. I think full duplex is good to be implemented in sub-6, below 2.4 gigahertz or something where there's a lot of scarcity of spectrum. Okay, but the spectrum is good in the sense that it has a longer coverage. So if you're able to double the capacity in those areas, it will be good. You don't have to implement full duplex in millimeter wave or at 6 gigahertz or 5 gigahertz, there is enough spectrum. Okay. So what are the network implications of full duplex? I mean, so while you don't, while to get an ideal full duplex node, you have to cancel all the self-interference, but to actually make the network better, you don't have to cancel the entire self-interference. For example, in massive MIMO kind of a solution where CSI feedback is a huge overhead, you can use the free full duplex channel to feedback your information. that would provide you huge network-wide gains. Okay, while it may not enable you full duplex, it can provide you gains in other ways that we have not imagined. Okay, it's just not about improving the throughput of your own node, but improving the throughput of the network can be done. Okay, but one thing you should understand is since you're transmitting and receiving at the same time, same frequency, is much more interference and more chaotic. It decreases a little bit, but the amount of gain you get in terms of the rate is close to twice. That's what these curves show you. The blue curves is the full in-band full duplex, and the red curves are the frequency division duplex. So what are the challenges? The challenges is, of course, self-interference cancellation. But as I pointed out to you earlier, we have to study at both the node level and the network level, whether is it really required to cancel all the interference, or you can use this a little bit more interfered uplink to do something better for the network. Okay. So currently, it's going to be, I mean, the initial studies are going to be based only on the downlink part of things, where the base station is going to be full duplex, whereas the cell phones are going to be still half duplex. Okay. So what is the implication of the interference in the network, increase of interference in the network? More system level studies have to be understood. Scheduling has to be rethought about a little bit. And the most important thing is hardware complexity. I mean, is this going to make your hardware so complex and so costly that you cannot implement this? It is my initial thought is no, we can implement this at a reasonable cost at the base stations, and it can give you a lot of gains in terms of spectral efficiency. So I want to conclude saying that this is a technology whose time has come. Already there's a lot of work that's going on in 3GPP. And I strongly believe that this is going to, I mean, this is the right technology in 6G, at least for the lower frequency bands. And we should do our part to enable this. So thank you.
Thanks all the guest speakers for wonderful presentations. Next, I'd like to open the floor for a discussion. My first question for this panel is, in your view, what are the main shortcomings of the 5G systems that could be addressed by 6G?
It's very interesting. I think very thoughtful question. I believe one aspect that it's important. I mean, I want to try to because it's multidimensional. Answer is I think multidimensional. One is how do you behave as serve verticals? And then actually, this is one thing that I think we have to be very careful about. I mean, verticals are very important for GPP. For those of us, like I myself, who've been in GPP for many years, and GPP was really effectively governed by cellular operators. And more and more we have now been balancing, I mentioned, between cellular operators and verticals. But then the truth of the matter is that we don't really see so far a very big deployment base for 5G on any vertical. Maybe we have to work to finding a couple of them. I think, I mean, everybody knows what are the verticals, but we have that, you know, the industrial, satellite, broadcasters, automotive. I think we probably are very close to see some satellite deployments based on 5G, maybe automotive also based on 5G. But there is, you have to understand that they play at their own. They go at their own cadence and their own pace. And I think this is something that probably there was a new team and really to do a better work serving them. So that's one area where personally I believe that apply some of the learnings of 5G towards the serving of variables. Another area I believe is trying to make the best use of the spectrum that we have, right? I mean, we have sub-6, we have, these advanced MIMO techniques, massive MIMO, which actually may extend a little bit higher. I mean, I mentioned that the 7.224 is right now uncharted, but I do believe that some of the techniques that are already used today for this sub-6 really enabling relying on, for example, the reciprocity of the channel, indeed taken to the next step on these higher frequencies, right? I mean, 6 meters and above, right? 7 meters and above. That's another one. And then talking about multi-antenna techniques, how many the way is deployed in a way that is more ubiquitous. I mean, from the point of view of actually, I mentioned earlier the different types of nodes, network nodes, how can we make deployment a little more economically viable and attractive to operators. And then also how is the entire lead management being done, both at the network side as well as the terminal, so that actually the communication link becomes as resilient as the technology that the people see allows you to be, right? I mean, it is, so all those things have been coming with the piecewise. I mean, with introduction of multi-panel, some of the multi-GRP kind of techniques. Those are, again, piecewise, one release at a time. And still, we will see some of those investments coming. And all these, of course, I hope in the new G, all those elements will be factored in from day one, in the same way that, manual was actually quite mature when we started LTE, because in 3G we have in the same way, the latter part of 4G LTE with this frequency and every manual, it works through this reciprocity based massive manual. And many other examples that they have. I mean, those are, I mean, certainly was actually allowed a little bit, and I'm expecting sharing, which if you think about it, a very powerful proposition that was brought in 5G, because the 5G enabled for the first time ever the soft refarming, right, of frequencies. But maybe it was a little bit underwhelming in terms of actual overall performance, right? I mean, where, I mean, something one could think that maybe you are better off even doing full LTE versus 5G right now. A carrier that has both, then it doesn't really get the best of both, and you get the worst of both. And I will be there for the first question. Thank you.
Yeah, actually, I'm not a wireless communication guy. Actually, I'm working mainly in computer science. To me, the 5G actually, mainly focus on wireless communication. Actually, it lacks kind of capability in localization, in sensing, and intelligence. That's why I'm thinking, how can we incorporate AI and the sensing capability, into the 6G network will be very, very appealing. Actually, in this regard, I have worked together with, the communication experts. Actually, in industry, in universities, we have trying to consider the joint design between, communication and sensing using the wireless signals. Now, either, we could study, for example, we could study, of course, the communication limit, the signal to noise ratio for communication. But at the same time, we also could consider, the sensing, range, the sensing limit, the sensing, kind of signal to noise ratio, those kind of fundamental research issues, so that in the future, we could bring intelligence, bring context awareness to different use cases. For example, right now, many companies, they begin to apply 5G in factory, in industry, in smart home, in different settings, in different vertical, areas. And in these areas, we do not only need wireless communication capability, connectivity, the capability, but also, more kind of intelligence to enable a lot of new functionalities. I think that's why I think, sensing capability, imaging, localization, and the intelligence AI, could really, bring a lot of new things. Thank you. Yeah.
Okay, thank you, Rakesh. And I agree with Professor Zhang. And first of all, I think 5G is successful. You know, 5G is a big step forward from 4G. And 5G extends mobile broadband to 3 usage scenarios, eMBB, MMTC, and URLLC. And 5G enables the communication industry to enter a variety of vertical industries. However, you know, for the year 2030 and beyond, more and more new services and requirements will emerge. But 5G was originally designed to focus on communication services, but not originally designed to support for information services such as sensing, and also computing services such as AI. Even for communication services, 5G is originally designed to eMBB, and then after that, 5G is enhanced and tailored to support URLC and MMTC on the basis of eMBB. So this is what I think is the main shortcomings of 5G. However, I think it is expected that 6G should natively support 3 services, communication, information, such as sensing, and also computing, including AI. And 6G should be designed to fully consider the needs of various use cases associated with the 3 services.
List is pretty much exhaustive. First of all, the spectral efficiency between LTE and 5G that was discussed, issues related to coverage, issues related to IoT, massive MTC, as it is being called as. You know, when 3GPP had to submit RIT as a candidate 5G technology to 3G, ITU, there was no other technology which was available. So for all practical purposes, Narrowband IoT was repackaged as a 5G MMTC solution and submitted as a SRIT. So, so practically speaking, there is no 5G IoT technology in existence. And there is some work happening in what is termed as REDCap, reduced capability devices. But that still cannot be called as IoT segment because it is primarily seen as some early effort to provide replacement for LTE as and when you take down LTE coverage. Otherwise, it's literally repackaging LTE devices as IoT devices. So that's where we are. I mean, there's quite a bit of gaps. If you look at some of the activities of SA6, service enablement, you know, one of the key factors in 5G was the integration or allowing the integration of verticals. If you look at 6G today, the activities of enabling certain APIs for certain verticals started much later in the day in the 5G specification process. So SA6 activity, which was supposed to enable this, it's primarily an afterthought. It was primarily a set of APIs which was cooked up and said, okay, this is it. This is how an integration of vertical can be done. No, that's not how things work. I mean, if you look at, go see the factory, they have a very complex system, and you know, we can use the system as some kind of a data connectivity. Now, we just look at 5G as a connectivity for any vertical. Now, why would I choose 5G? I have alternate technologies as well, which is something that, you know, enterprises do ask. So it's a natural question. It's just connectivity. I have multiple forms of connectivity, secure means of connectivity. So these are some of the key challenges that we see in 5G that has to be addressed in 6G. I mean, I can go on into some of the specifics, but let me stop here.
So, I mean, since my presentation today is about AI ML, right? I was thinking about, so the 5G and 6G. I think 6G, 5G, I think has some flavor of kind of adaptation and learning in that picture. But I think actually machine learning and AI can play a major role, a very important role in 6G, especially a lot of things which, let's say, adaptation and actually configuration-wise. But on the other hand, how to apply it? There are challenges. We did actually see those challenges, and That's why if you look at the last sentences, really we want to, right, apply it in a smart way, relevant province. We don't want to reinvent the wheels.
Yeah.
But on the other hand, I think actually AI ML can be helpful, very helpful.
Yeah.
So just to highlight what are some of the drawbacks of 5G, one big drawback of 5G, as Satish has pointed out in his talk, is that MMTC was never an integral part of 5G. While the use case has been talked about a lot, somehow the standard has not evolved MMTC when the initial deployments are happening. Okay, of course, there's a lot of roadmap for this, but by the time NB-IoT is being taken up by all the deployments, that's one thing. And second thing is massive MIMO. Okay, massive MIMO, while it's very nice and there's lots of advantages to it, there are lots of challenges in terms of both implementation, in terms of channel feedback. These issues are not yet resolved. Okay, these issues were there in 4G, they are still being carried out to 5G. Until unless some significant work is done on this, I will again increasing the number of antennas, I don't think will matter. Okay, I'm not seeing channel hardening or anything happening in 5G as of now. And second thing, a more personal comment, what I feel is that the specification for 5G is extremely complex. Okay, so going forward, if we want wide adaptability of 6G, okay, of 3GPP standards, the complexity of the entire spec has to go down. Okay, you don't require so many moving parts to build a very nice specification or very nice standard. Okay, too many things that happen in 3GPP which will never see the light of the day, but they make the specification extremely complex for both implementation, understanding, and interoperability.
My second question for you is, compared to 5G, what would be the most significant technical features in 6G?
AI is a project that I guess we both are involved. It's going to be a very important sandbox for future people and for companies to realize how much early we need to face standardization, we need to specifications, right? I don't believe anybody has an answer, but we believe there is a value to create an interface from day one, with the understanding that there will be this possibility to enable AI/ML based implementations. Which so far, those are, most likely, pretty much every network vendor or terminal vendor may have its own ways to use this data analytics to improve their own algorithms, and then actually try to find ways to improve the user experience, which is the objective. Actually, network energy savings for that matter. But it's an afterthought, right? I mean, the interface is fully unaware. And then we are now trying to do both the network interface, how the network interface could be augmented to enable this better implementation of this AI ML type solutions. I mean, again, I'm absolutely believer that from day one, you already know that you have to enable that possibility. Food will be more naturally towards those implementations. We will see how far we go with 5G implementation, but I think certainly that will be useful for 6G. That is probably one very important area. On the rest, I think it's and I've been involved on cellular since the 2G days. 2G was very successful in general, like GSM 995. 2G was very configurable, right? I mean, it was a really cool box, as people said, it rules to get it to play because of the complexities. 4G was a huge success story. And then, but it was very monolithic. And then 5G, I remember the early days of 4G communication, configurability was almost a taboo. We did not need to configure because it was adding complexity, adding testing, right? A lot of things that were not received from the 3D learnings desirable. I mean, I really felt that for 5G, there was a bit of a forgetting factor, and 4G, 5G, again, everything became configurable. One could argue that 5G has to be configurable because of the different very diverse use cases that were diverse spectrum. But maybe we went too far in making it. And then that could also be the reason why verticals are having some difficulties in taking 5G for their own use, right? Because they don't really know how to configure it for the verticals. And maybe there are only few people on Earth who know how to do it, what would be best for them. And these are where maybe in CG we could do a better job, right? Understanding that we're going to be overboard into configurability and then all the things that this brings later, whether it's testing or even implementation, makes the whole ecosystem confused and then actually not good for the end user. Yeah, so I'll leave it there.
Okay, thank you. Yes, and I think the system functional framework of 6G shall be designed to fully and natively consider the needs of various use cases associated with the three services, including communication and sensing and also the computing. Based on the redesign of the system functional framework, the converged communication and the computation network can better provide computing and AI services. And additionally, the native AI network puts AI into action in the network to improve the network and air interface efficiency. And also the integrated sensing and communication, just said by Professor Zhang, can better provide sensing services. And besides, I think the introduction of the technologies such as the MIMO evolution, the RIS technology, and the very low power or zero power communication, and some new waveforms, for example, the delayed Doppler waveforms, and these technologies can be helpful to improve the energy efficiency and also the spectrum efficiency, and they can work together to better support the communication and sensing and also the computing services for the 6G. Okay.
Yeah, so in 6G, we don't have a doubt that AI will be used in a far more comprehensive way. That is for sure. It's going to happen. When we look at ITU and some of the discussions in ITU, there seems to be a lot of consensus coming in that direction, which is fine, great. There is a lot of consensus as far as the sensing part is concerned as well. There is some kind of sensing will also be inbuilt into 6G physical layer communication aspects, which is also fine, I think there is a lot of consensus around that. What is not being discussed comprehensively so far from 6G perspective is the network architecture. If you look at the centralized network architecture today, it's from the 2G days, same thing. You have a SIM, you have a device, you show up a SIM card in a SIM slot. And that's the nature of the business. And we do have eSIMs now, but essentially the validation of the eSIM happens at the core network. So essentially it's a centralized architecture. And though there is a lot of discussion about private networks, there are tons of issues which needs to be handled. A lot of press releases are coming. You see a lot of press releases. It's all fine, but the reality of ease of deploying 5G for private enterprises is still there, because all the way from spectrum is something which is well understood. But then who owns the SIMs? Who will buy the IMSIs from the government? Because even that is regulated. All those issues are there. Availability of device, as I told you, 5G doesn't have an inherently doesn't have IoT technology inherently. It's just narrowband IoT plus plus. If you look at device ecosystem today, you do not have, at least I've not come across, modems which will give you 5G plus narrowband IoT. No. So essentially, when we talk of private networks from a 5G perspective, there are issues. There are issues which are practical issues. So 6G, if it has to really enable native AI across the protocol stack, and AI needs data. AI just cannot be just, you cannot just embed algorithms across the board. It needs data. It needs, if data has to be there, then data has to be centralized in different entities of the architecture which exists today. There is a core network, there's a RAN network. There's only data in the core network. There's not much of a data in RAN network, but obviously then we're talking of bringing data into the RAN network as well. All of these things will have to be accommodated. Coreless RAN is also something which is being discussed predominantly from an IT perspective. Architecture is the central entity. If you look at 6G, it has to be the central entity, which of course will also take into account sensing, which means there's a lot more activity to be done at the scheduling part, standardization to be done at the scheduling part. Your radio resource management is not as simple as such because now you have sensing. One should also have the architecture which takes data hierarchies into account, which naturally brings AI into the hierarchy. Thank you.
Okay, yeah, actually, I really, agree with, the remarks from the previous two professors. Actually, when the 5G is, when is moving towards 6G, we have, maybe more bandwidth. We have, we could use very high frequency spectrum and so on. We could also introduce, for example, intelligent surface, maybe into the picture. In such a way, we could also, improve the sensing performance greatly. Because with large bandwidth, with high frequency, kind of spectrum, and with also, the intelligent surface, we could really allow much higher, localization accuracy, sensing performance. And just now also, just now Dr. Dajie Zhang also mentioned, the integration of three resources, communication, sensing, and also, computing. Actually, when we want to incorporate in AI into 6G, we need a lot of data, we need a lot of computation. In such a way, we need to consider the computing resources allocation. In such a way, we need to maybe either, need to consider cloud and the edge intelligence into consideration, and also, need to consider the trade-off among computing, communication, and the sensing. Actually, I think the 6G network, wireless network, would consider all those factors and have a much, bigger gain, compared with 5G network. Yeah, thank you. Yeah.
I think AI ML will play a role, but how significant it will, I don't know. On the other hand, I think actually another area I'm actually personally interested in, also spending quite some time exploring, is the non-terrestrial networks. Mm-hmm. So actually, I think now maybe we kind of pretty much saturated with terrestrial network, where actually now we have we need another dimension, right? We need the z-axis, right. X-axis, y-axis is there, z-axis, and that is something I think can potentially be a relatively kind of game changer. And on top of that, of course, AI ML, because the main issue about AI ML is that there are a lot of issues where non-terrestrial network, where actually traditional signal processing can still play a very important role, kind of model-based approach. But 6G is still too early to say, right? So,
yeah.
And of course, enhance of those MIMO operations is very important. I think I don't know how 5G. I mean, I was told 5G MIMO needs to be improved, and especially millimeter wave, right? I mean, it's not that, let's say, successful as we expected. So, and there are a lot of things probably needs to be done at that as well. Yeah.
Yes. Yeah.
So for 6G, what I believe is AI is going to play a very critical role. And I hope that AI is also going to design the protocol. Okay, so this a lot of this overheads in terms of pilots and all these things will significantly reduce. I mean, I believe that AI is going to play a critical role. Of course, there's going to be huge data integration, sensors integration. Okay, sensing is going to become part of 6G. I mean, that's what at least it looks like. The third thing, at least I hope that happens, is that higher frequency band, specifically the millimeter wave frequency band, is going to get really utilized for 6G. Okay, terahertz. I mean, I have my doubts about terahertz being utilized for 6G in a realistic manner, but at least I feel that millimeter wave technology will become much more mature by that time, so that the sensing applications as well as high throughput data rates are going to actually become a reality in 6G.
Thank you all. And with that, we will wrap up today's discussion. A huge thank you to all of our panelists for the insightful presentations, and to all of you watching this virtual event. We are grateful for your time and attention. Today's discussions were inspiring, and I'm looking forward to seeing what the 6G future holds. Have a great evening. Bye.